This is the largest plane in the world.
The Antonov is unmatched as far as how extraordinary of a flying machine it is.
I thought, how is that possible? A wing as long as a football field? No way this thing can fly.
The Antonov AN-255 is unique. It's set over 200 world records and has a huge global following.
It's sort of a spectator sport when people come out to watch the Antonov take off and land.
This aircraft is huge. It even dwarfs a Boeing 747.
With a maximum takeoff weight of close to 800 tons, it's so incredibly heavy, it appears to defy science. So what extraordinary feats of engineering enable it to fly? The only way to find out is to look inside it. The giant Antonov AN-255 is a cargo plane like no other. Its role? Transporting the heaviest air freight on Earth. In May 2016, it undertook an epic journey, transporting a huge industrial generator from Prague to Perth, Australia. Public interest was so high that a German news crew filmed it every step of the way. Dmytro Antonov is in charge. He's not related to the company founders, but he is one of a select group of pilots qualified to captain the plane.
We are carrying some very heavy cargo. For example, to Australia we are bringing a generator. We have so big cargo and now we'll fly with this cargo. How is possible? But I know it's possible.
This
Antonov is the only plane that can load over 100 tons. The generator weighs 117 tons.
That's the weight of 18 African elephants. And transporting it by air is super expensive. Hiring an AN-225 costs about $30,000 an hour. For that, you get the largest plane in the world. If you were to park it in a soccer stadium, its 290-foot wingspan would reach over both touch lines. And its 275-foot fuselage would stretch from box to box.
It's unique, only one in the world, and the biggest, still biggest plane in the world.
The first challenge is how to get the generator into the fuselage. Remarkably, the front of the plane is hinged.
The Antonov AN-255 is so cool. Because the nose lifts up, it gives you quite open access to the entire cargo bay, so you can easily load things in.
Precision hydraulics lift the normally sealed nose and open the fuselage like a giant mouth. But it's too far off the ground to load into directly.
It kind of bows down in order to swallow the cargo. It's almost like a big snake that like unlatches its jaw and then comes down to the ground to like eat its prey.
The leading undercarriage pylons are jointed. And as the fuselage lowers, a ramp unfolds, allowing an 11-strong team to crane the generator into position. The AN-225 has a maximum takeoff weight of 800 tons. With cargo and fuel on board, it's not far off that now, and will be heading down the runway in less than an hour. The 225 wasn't originally a commercial plane. It was designed in the 1980s at the height of the Cold War. The Soviet Union's military had begun a clandestine program to develop a space shuttle to rival America's, and they needed an enormous place to transport it.
At the time, it was not public at all. It was all top secret. No one knew about it.
The Soviet shuttle, known as the Buran, was far too big to fit inside any existing fuselage. So the USSR invited Ukraine's finest designers and engineers to take up the challenge.
We were all so excited. We had sparkles in our eyes, filled with the desire to put in as much of our knowledge and abilities as possible to find the best solution for this aircraft.
They knew they had to design a plane the likes of which had never been seen before.
I can only say that obviously the most complicated part was to design this wing.
The wings needed to be vast, but where they're positioned is also critical. Civilian planes have wings mounted as low as possible.
They're attached to the bottom of the aeroplane, and you'll see that the wings are slope upwards from what we call the wing root. And the reason for this is dynamic stability and control of the aircraft. And we call that upsloping wing dihedral.
This means that if, for example, a gust of wind pushes the aircraft and it rolls in one way, the aircraft naturally wants to stabilize itself.
In the case of the AN-255, another similar military cargo type aircraft, the designers use an anhedral wing shape, which is the wings sloping down from the center of the airplane out to the wingtips.
The reason is that carrying heavy loads negates the need for the extra stability that an upwards dihedral angle would give.
But also the wings look more anhedral than they're going to be in practice when the plane is flying, because the wings are flexible. And when the wings get loaded by generating lift, they actually will rise up a little bit. So the anhedral angle is to kind of balance out the natural deflection you get of the wings under lift, so it kind of evens out to about level.
When the AN-255 took its maiden flight in 1988, it was a tense moment.
This is so much bigger than anything that had flown and was flying at the time. The engineers who'd created it must have had some trepidation about whether or not their creation was actually going to get airborne.
It's very difficult to express your feelings. You know, this feeling if your heart stops and knots build up in your stomach. But I can tell you, the delight from seeing how the aircraft smoothly, beautifully, slowly, literally, graciously takes off.
The AN-225 soared into the sky triumphantly and took even its engineers by surprise.
I thought, how is that possible? A wing as long as a football field? No way this thing can fly.
The plane went on to prove it could also fly with the shuttle on board and was nicknamed Maria, Ukrainian for dream.
The plane was unveiled to the public in the Paris Air Show 1989, and it really stole the show.
I remember looking around and seeing that the queues of people to see Maria was larger than the rest of the audience combined together.
I was walking around all puffed up with pride, and I let everyone I met know that I'm a test pilot.
For Ukraine, it was a historic moment. Like never before, the then Soviet country led the world.
I always talk about our constructors with such pride. Those people are outstanding. They are the gold of our nation.
But the halcyon days were short-lived. When the Cold War suddenly came to an end and the Soviet Union collapsed, it was curtains for the Soviet space program, too.
Sadly, the AN-255 became surplus to requirements and was mothballed. There was a distinct possibility that this amazing machine, of which there was only one, was going to be allowed to rot, become dismantled, fall apart, and never take to the air again.
After being left to rot for years, the largest plane in the world comes out of retirement. In 2001, the Antonov company spots a gap in the market. About $20 million is spent on a refit, and the AN-225 becomes the most spectacular civilian cargo plane.
The floor is strengthened for transportation of heavy cargoes. We have lightened devices like chains, which are nowhere near as heavy as in previous aircraft. The locks are screwed down into these holes, and we fix the cargo so that during the flight it doesn't move anywhere and is safely fixed inside the aircraft. With the help of the winch, we can drag any cargo inside here. The winch can be positioned anywhere on the floor.
The cargo hold is enormous, 20 feet wide and 141 feet long. That's longer than the distance the Wright brothers flew on their famous first powered flight. And just enough room for the AN-225 to set the world record for the longest cargo ever carried by air.
We are sometimes getting very interesting one piece of blade wind turbine. It's 10 tons, but it's very long. No other can do it. They can do it by sea, but it's long time. It's maybe 1 month to carry this blade.
Every loading is a challenge, I would say. This plane is not ordinary, and its cargo are not ordinary, so it's always tricky to load it.
The conversion is a triumph, enabling the plane to swallow up all kinds of giant cargo, and even the heaviest air freight ever.
All crew feeling very proud, all personnel proud to be a part of the team of this plane.
In September 2001, the AN-225 carried not 1, but 5 battle tanks, serious heavy lifting, and a world record load of over 300 tons. Somehow, they all fitted into the fuselage.
I remember, I was there, helping to drag in, adjust and secure the tanks.
Their total weight was around 250 tons. Actually, I think they weighed a bit more. And we lifted this weight to an altitude of 10,250 meters.
These record loads are far heavier than the 128-ton space shuttle.
In its new role, the structural stresses on the aircraft would be really significant.
Luckily, the 225's original designers had cleverly over-engineered the wings.
It's hard to believe that something that large and that heavy can ever lift up into the sky on its own.
The designers knew that their plane should generate more lift than any other in existence. It was completely uncharted territory.
There are 2 ways you can get a wing to generate more lift. One is you make it move through the air faster, or you make it bigger. they realized that they would have to have wings that were bigger than anything that had gone before.
The broader a wing is, that is, the more area it covers, the more total upward lift you can get. But the Antonov's wings are actually wider than the length of the plane. Every piece of that wing is now adding to the lift that it can supply to lift the whole plane off the ground.
Enormous wings, though, add even more weight and create a potentially disastrous weakness.
As you make a longer and longer wing and that is experiencing lift, you're putting more and more load on the wing.
The largest loads in any wing are typically around about the wing root, so where the wing joins in with the main fuselage of the aircraft.
Dmytro gets the go-ahead to begin his 4-day mission to fly this huge generator to Australia. The AN-255 thunders away from Prague.
I'm flying about 14 years. Flying in the biggest plane in the world, it's an amazing feeling.
With his super heavy cargo and wings this long, it's a mystery the wings don't shear off at the stress points where they join the fuselage. The answer is hidden inside the wings. Underneath the aluminum skin is a regular arrangement of ribs, but in the central section, there are 4 large reinforcement beams. These prevent the colossal lift force acting on the joints by fixing the wings together and spreading the load. Inside the Antonov hangar in Kiev, Ukraine, a second AN-225 lies half-built, with the inner structure of its wings exposed.
You can see how one of the beams of the fuselage reaches the center section and is attached to the girders of the wing. You can see the attachment. This is what guarantees safety from the load the wings put on the fuselage.
After flying roughly a third of the journey to Perth, Australia, Dmytro brings the AN-225 and its huge generator cargo down to fill up in Turkmenistan, where jet fuel is known to be cheap.
Well, the AN-225 is burning 15 tons of fuel per hour, so fuel cost is quite significant.
This plane burning every hour more fuel than, for example, Boeing 737 have for whole trip.
Refueled and back in the air, the next stop will be Hyderabad, India. But a hydraulics problem is about to threaten the mission.
Getting spares for a true one-off aircraft such as AN-225, whether you're in Hyderabad or wherever in the world, is always going to be a challenge.
The largest plane in the skies, the unique AN-225, is en route to Perth, Australia, where it's due to deliver this massive 144-ton generator in just 3 days' time. Next fuel stop, Hyderabad, India. The news crew filming the journey capture a crowd of fans flooding the runway to witness the event.
It's an honor to have it over here and coming in the South Asia Pacific region for the first time. So it's really a matter of pride for us.
Dmytro is fast becoming an international celebrity.
I remember one more time in Honolulu when I first coming to Hawaii. It's approximately the same. We have flowers and but without the stick on head.
The crew suddenly discover all is not well beneath the wings. There's a problem with the hydraulics, a major concern for flight manager Vitaly Shost.
Not broken. As I said, it doesn't work properly in this case, but it's not broken.
Flight plans are hastily rearranged and the crew rush to make repairs. If they're unsuccessful, the delivery will be abandoned.
We are trying to solve this issue.
The crew are forced to disembark, and burning through a $30,000 per hour rental fee, the client is getting anxious.
It makes my job more difficult, you know, because I need to drop my things, my retired things, and pay attention to all of them. But still, nobody rejected me to do my official duties.
Hydraulics play a vital role in the AN-255. One of their functions is at the heart of how the plane maneuvers in the air. On small planes, control surfaces, like the ailerons on wings, are physically linked to the cockpit. Levers mechanically transmit the pilot's commands to the control surfaces. But on the AN-225, that would be impossible because those control surfaces are so large.
If you imagine the forces involved in opening a door into a hurricane force wind, you get an idea of the kind of forces you're going to need to push on these surfaces.
The solution is known as a fly-by-wire system. The genius of this is it eradicates the need for the pilot to have any mechanical links to the flaps.
A fly-by-wire system enables you to have the cockpit and have the controls at the cockpit connected electronically back to the actuators that turn the control surfaces.
Behind the cockpit is an array of computers. When the pilot operates the controls, the instructions are processed electronically and then sent down hydraulic lines. These fluid-filled pipes are connected to powerful hydraulic pistons called actuators, which deliver the force needed to move the huge control surfaces.
The hydraulic system takes advantage of Pascal's principle, where the pilot can put in a relatively small force, but pushed over a large distance, and through the hydraulic system, that gets translated to a large force, but over a smaller distance, a little bit like the way a lever works.
Hydraulics also play a crucial role inside the plane's unusual tail configuration, a consequence of being designed to carry the Soviet space shuttle.
The Buran is attached to the 225 here on these humps.
Carrying the Buran outside the fuselage threw up a significant aerodynamics problem.
Well, trying to fly a plane with something as enormous as a Buran space shuttle on top of the fuselage is, of course, very challenging. And one of the major challenges is the fact that it disrupts the airflow that would take place as you move down the plane. And that's normally where the vertical and horizontal stabilizers would be.
When a model plane was tested in a wind tunnel with the Buran on top, there was too much buffeting on the tail.
So if you arrange the space shuttle right in front of the vertical stabilizer, the rudder of the plane, the rudder may not be as effective.
The turbulence would make the plane virtually impossible to maneuver. For the Ukrainian designers, a single tail fin had to be rejected.
So what they did is they actually used two rudders outset from the fuselage in order to get outside of that disrupted airflow, so it could still fly effectively even with a space shuttle on its back.
Now the trail line from the Buran will pass between them without causing buffeting.
The twin tail solves one problem, but it creates another.
Now you've got to have two separate rudder systems which you've got to work in a coordinated sense and move together in order to control the aircraft correctly.
Engineers avoided a major design fault by installing two sets of powerful hydraulic actuators that are linked together electronically. Sensors monitor their relative positions, guaranteeing that the actuators move both rudders or both elevators in unison.
In flight, I believe it's like other else aircraft. Flying, it's very light control, it's good.
But that's only when the hydraulics are working properly. If they're not, the pilot risks losing control.
We took off once and were passing Europe when we lost hydraulic liquid from the second system. We carried on flying. When liquid left the second system, it started leaking from the third system. That became dangerous.
Often, planes have three parallel hydraulic systems, so that if one leaks, others can take over and maintain control.
So I made a decision to land at the closest airport. When we landed, we were down to the last few liters of liquid.
This remarkable escape was down to the Antonov's extra redundancy, an additional backup hydraulic line.
We have 4 hydraulic systems, so if one fails, it's not a big deal.
In Hyderabad, the AN-255's hydraulics have been fixed, but local air traffic control can do nothing to speed up its departure.
We will be late with departure because of all of this. Maybe I will have problems with my management because our policy is just to keep the schedule. It's my fault. I should have known. I should have known it.
Dimitro and his crew have no choice but to wait for a takeoff slot. But what they're unaware of now is that at their next stop-off in Kuala Lumpur, they will encounter every crew's nightmare.
We have to remove the part.
Engine trouble. May 13th, 2016. The enormous Antonov AN-255 is on a $3 million contract to deliver this 144-ton generator to Perth, Australia. Time is critical, but the plane has been held up in Hyderabad.
We will be late with departure because of all of this. It's my fault. I should have known. I should have known it.
After a long wait, Dimitro gets a green light to fly on to the next fuel stop in Kuala Lumpur. When the AN-225, aka Maria, touches down in the Malaysian capital, engineers unfortunately discover a serious problem with one of its engines.
We have to remove the part, or it'll overheat.
The mission is in trouble. This could be a disaster. The Antonov won't be allowed to fly unless all its engines are working.
We can't connect it.
But exactly what does it take to get a plane this heavy to move fast enough down the runway to get off the ground?
An aircraft that weighs 705 tons at takeoff requires an enormous amount of thrust to accelerate it.
Antonov designers knew a regular set of engines would be inadequate, and they didn't have the money to invent a new engine. So they looked to the turbofan jets on an earlier cargo plane called the Ruslan.
The first engines were installed on Ruslan, and the same engines were installed to Maria. It was the first time in the Soviet Union that such an engine was developed, an engine of such size and dimensions and such capacity. The D-18T engine's thrust on takeoff is 24 tons.
These D-18T engines are high bypass turbofan jets designed to produce more thrust than a standard jet.
Turbofan engines produce thrust through basically a combination of two mechanisms. So first of all, it is a gas turbine engine combined with essentially a fan, turbofan.
So there are two ways you can increase the thrust. You can increase the speed of the air that goes through your engine, or you can put more air through that engine.
These put more air through the engine. As with a standard jet, there's a combustion chamber that delivers thrust by expelling exhaust out over the turbine at the rear.
That turbine also drives a fan, which is housed at the very front of the engine.
This is the clever part, the turbofan. As the turbine spins, it spins the huge fan at the front of the engine. This sucks in a massive volume of air and sends some outside the combustion chamber to these bypass channels. This air is then accelerated out the back. Incredibly, 80% of the engine's thrust is produced by this bypass.
By having that big area of the fan putting out the air, even if it's at a lower velocity, it's such a big area, it's still moving a lot of mass, and it's more efficient than just using a pure jet engine.
These engines are really big and very powerful. They have around 70,000 horsepower. Now that's equivalent to over 400 average cars each.
The Ruslan has 4 of these engines, but for the AN-255, the Maria, 4 would fail to produce sufficient thrust.
They made an extra center section of the wing so they could fit more engines. So instead of 4, there are 6. That means their total thrust on takeoff is over 100 tons. Can you imagine? That's the capacity of these 6 engines.
Dmitro and his crew are still stuck in Kuala Lumpur, waiting for one of his 6 engines to be fixed. They need to take off soon, or they stand no chance of arriving in Perth on time. Both money and reputation are at stake. For 30 years, the AN-255 has had a devoted cult following. While crowds start to assemble in Perth for the rare chance to witness the AN-225 landing in Australia, the plane is still stuck on the tarmac in Kuala Lumpur. They've had engine trouble. But after a lengthy hiatus, it's fixed, and Dmitro gets ready to take off on the last leg of the journey.
Виталий, кетеринг. Через 15 минут по полету.
But there's another hitch.
Just waiting, no flight plan in the system in Kuala Lumpur Tower. We're waiting. Vitaly calling to office about this.
Out of the airport. Поеду. Okay, can I go? To the briefing. To the briefing. You will take a long time. Out of the airport.
It's not our fault. This flight plan was filed 5 hours ago. It's the fault of Malaysian air traffic controllers.
Tell me.
Eventually, the crew negotiate a new flight plan and clearance to take off at last. Another 2,600 miles and the AN-255 will reach its final destination in Perth. Landing this sky monster, loaded up with 144 tons of cargo, is the most critical part of the mission. How on earth can the plane land with all that weight without smashing into pieces?
Typically, the landing part of any flight, and certainly an aircraft, for an aircraft as large as the Antonov, landing is going to be the most dangerous part.
It's going to need a significant amount of runway in order to come to a stop, up to 11,000 foot.
But touching down safely anywhere for this super heavy behemoth of the skies is a procedure fraught with risk.
If you ever look at a commercial aircraft, you know, the wings deploy down and it basically makes this huge sail in order to redirect the air in a different direction and catch that air and slow the plane down.
Fine control of the approach speed is critical. If it's not perfect, the landing must be aborted and reattempted. It's known as a go-around and can add thousands to the bill.
We know exactly our performance, and I can calculate what exactly landing distance need to, for this weight.
After flying more than 8,000 miles, the AN-255 has to make just one more landing at its final destination, Perth, Australia. Its colossal weight presents a particular engineering nightmare at the moment of touchdown. A regular undercarriage could buckle on impact.
If we will land all landing gear in one time, it's a little bit bump. It's not good for a plane.
And that's all about distributing the weight of the plane over many tires instead of like one tire that could easily blow out.
Dimitro knows that to bring the plane down safely, there's little room for error. The AN-225 approaches the final destination of its long journey, Perth, Australia. It's the plane's first visit here. And as with any landing, the moment of touchdown is critical.
The Antonov undercarriage is amazing because of its sheer scale. It's made up of 32 wheels.
The unique undercarriage arrangement is normally hidden during flight inside the massive fuselage. 8 rows of struts hold the incredible total of 32 wheels to spread the force of the impact. But the real secret for softening the landing is the state-of-the-art suspension system. Each wheel is mounted on what's called an oleo strut, a high-performance oil and gas combination shock absorber.
That is like a piston inside of a tube. And inside the tube is a combination of nitrogen gas and oil which together allows some sort of elastic effect, but also a viscous damping effect when combined.
Landing also puts huge stress on the tires. The 225s experience so much friction, they heat up to 250 degrees Fahrenheit. What's to stop them from exploding?
So these wheels are made of rubber reinforced with a steel mesh, which makes them really, really strong. And even if one of them were to fail, they're filled with nitrogen, so it wouldn't be a catastrophic explosion if it did fail.
But they do lose a lot of rubber every time they hit the tarmac.
These tires need to be replaced every 90 landings, and every time you do that, it costs $1,000 per tire.
News of the giant Antonov's imminent arrival in Perth has now brought traffic jams and a 30,000-strong crowd to the airport.
It hadn't been there before. It caused such a furore. People knew Murillo was going to arrive, so they were waiting there for a few days. There were thousands of people.
To the delight of the spectators, Dimitro pulls off a perfect landing.
Alpha Delta Bravo 3610, welcome to Perth.
Massive. It's well worth coming down.
That's pretty impressive, eh? It's good fun to see something a bit different.
To see it in real life is just mind-blowing. You have to be here to see it.
It was really, really exciting. It's probably about the best thing and most awesome thing I've ever seen.
After landing, we see person staying around airport near the fence, and with photo. And in this moment, we are all crew feeling very proud. All person proud to be a part of the team of this plane. It's an amazing feeling.
The huge generator can now be offloaded just a day late. And a group of Ukrainian expats celebrate with the exhausted crew. Whatever the future holds, the Antonov 255 is a unique plane that soared into the air from behind the Iron Curtain and shocked the world with its huge size and unrivaled capabilities. By taking it apart, we've discovered how it defies gravity and takes to the skies, and how it carries cargoes no other plane can lift.
As the plane passed by us and asked, "Oh, what is the plane?" It's Antonov 255.
The Antonov AN-255 is probably adored the world over because in terms of sheer size, it may never be beaten. This is no ordinary ship.
It's one of the biggest in the world.
To carry some of the largest sea cargoes ever, it does what most ships are designed to avoid at all costs.
It's really amazing to see something this big immerse itself almost completely underwater and then come up again, carrying something huge.
It's a bit of a game changer. It's like kind of a combo cargo ship and submarine.
The GPO Amethyst is one of a prestigious superclass of ships known as semi-submersible heavy lifters.
To be a captain on this vessel is actually a great honor.
From the outside, it's impossible to see the feats of engineering that give the Amethyst its incredible capability.
So a lot of factors can go wrong, and we should be ready for any of this.
The only way to reveal its secrets is to take this supership apart and uncover what's going on inside. Today, the Amethyst is en route to the Gulf of Mexico, where it will attempt to load up 2 giant decommissioned oil rigs bound for Oman. At the helm is Captain Yevgeny Nikityuk, who's been in the ocean-going heavy lifting business for 11 years. The next few days will see his ship tested by not only some of the biggest cargo on the seas, but also by weather that pushes them to the brink of disaster.
We have 7 squalls appears, with wind speed up to 55 knots.
In recent years, global industries like oil and gas have demanded ever heavier cargo to be transported across the globe. Single items can weigh up to 50,000 tons, and that creates a real problem.
The weights of these things is just absolutely mind-boggling. Just imagine trying to move that from A to B. It'd become almost impossible. Things like road and rail, you just can't move a modern oil rig like that. And the old solution of dragging them using tugs just wasn't cutting it. So an entirely new approach was needed.
The only viable solution is to transport these exceptional cargoes by sea. But to do that requires an exceptional ship. Enter the Amethyst, one of heavyweight ocean transportation's most advanced vessels.
This is a class of huge heavy lift ships, and they're just awesome in scale. They're enormous, and they can lift things which are so heavy you just can't lift and transport them by any other means.
I find this type of shipping very, very interesting. Each project, each cargo is totally different. We are loading and discharging cargo all over the world. And it's just an amazing type of shipping.
This ship's deck is an incredible 600 feet long and 158 feet wide. It's so big that no less than 16 Statues of Liberty would fit onto it. The deck can also accommodate both of these enormous oil rigs that tower over 200 feet above sea level.
Imagine trying to move a massive oil rig weighing tens of thousands of tons. And worse than that, it's not a tall hydrodynamic. It's not got a beautiful, sleek hull like a boat. It's basically a massive square. So moving these things had become more or less impossible.
As the Amethyst approaches the rigs, the 26-strong crew prepare the deck for the colossal cargo.
So now they are putting the stagings down on the main deck.
The rigs have a combined weight of 25,000 tons. And that presents a fundamental engineering challenge.
Now, the most obvious problem of carrying such heavy cargo on the deck of a ship is the strength of the deck itself.
The Amethyst has a very, very, very long deck. So when it tries to pick up a load, if the load was very heavy and just concentrated right in the center of the deck, it might try to taco the whole ship. The front of the ship would hit the back of the ship.
A deck of very thick steel would stop it from caving in, but it would also make the ship far too heavy. In fact, it has a very thin deck.
The thickness of the steel is tiny compared to the area. Without any additional stiffening, it's going to buckle like a piece of paper under these loads.
The solution comes from dry land, from inside skyscrapers. The deck is only an inch thick. But underneath it, there's a lattice structure connecting it to a second thin deck. The lattice is comprised of very specifically shaped steel beams. Their cross-section is like a capital I, just like the I-beams that hold up skyscrapers. Even when immense force presses down on them, the shape should prevent any distortion and protect the thin top skin of the deck.
And that's going to increase the stiffness without increasing the weight very much, because at the end of the day, this vessel needs to float.
The next problem is how to distribute the load across the deck.
It's really important that the cargo deck remains flat, because if it bends slightly and part of the deck is higher than another part of the deck, that load will all sit on the highest part of the deck momentarily, which could break the ship.
At a shipyard in Kaohsiung, Taiwan, GPO are building 2 more heavy lifters with the exact same design as the Amethyst. And they're in the midst of constructing the super strong ultra-flat decks. Giant piles of steel plates are being prepared. "154 of them need to be fixed together. That's 1.5 miles of seams to be precision welded."
Welding steel plate is very challenging, but it's necessary for a ship like this.
We use carbon dioxide arc welding to make the joints, because it's fast and gives a really smooth finish.
Once the welding's complete, the deck is inspected.
Yeah, this deck should be extremely flat for the cargo operation.
Shipbuilding doesn't usually involve measurements in tenths of inches, but for these ships, it's vital.
Acceptable limit for the deck is a 3.54 milli for our deck. Now it's absolutely okay.
These vessels will be complete in roughly a year's time. Back in the Gulf of Mexico, Yevgeny is racing to rendezvous with the cargo.
Other port. 090, steady.
The Amethyst must have an extraordinarily powerful engine system to maximize its speed. The question is, what? With a total length of 738 feet, a breadth of 158 feet, and a height of 20 stories, the Amethyst is vast. It needs to be to successfully pick up its consignment, these 2 massive decommissioned oil rigs.
Там вообще нет опций, там только safety коридор. Все.
Captain Yevgeny checks his radar.
We're just trying to locate where the first rig is now.
He's closing in on the loading location near New Orleans.
It's on the starboard propulsion, on the port propulsion. 420.
Once the rigs are loaded, the Amethyst needs to carry them more than 13,000 miles to Oman as fast as possible.
These vessels are operating, transporting very expensive drilling rigs, for example, and the drilling rigs, very expensive day rate. So time is very important.
It's crucial that nothing goes wrong with the propulsion system, so Chief Engineer Konstantin has a computer system to monitor it.
My role here is I'm responsible for all equipment. Что вы там крутите? У нас съемки идут. Ну, на одном посмотрите, на остальных не надо.
There's only one choice for the main engines. Diesel power remains the standard. And for a ship this size, the engines need to be gigantic. One is not enough, so it has a pair on either side.
This is our main diesel engine. For this ship, we have 4, like this one.
Each engine is around 9,600 horsepower. That's the equivalent of 12 Ferrari V12 engines. You know, these are really, really powerful engines.
Extreme power means extreme weight. Each engine weighs 132 tons. The 4 of them together are heavier than a jumbo jet. But curiously, these engines are nowhere near the propellers.
In most ships powered by diesel engines, the engine is connected through a gearbox to the propeller shaft. But in this ship, the engines aren't physically connected to the propellers.
The engine's massive size means the only place they can fit is at the bow. But that means a 540-foot-long drive shaft, connecting the engines to the propellers, which can't be done.
One issue with having a 540-foot-long drive shaft would be that it would need to be supported all along that length, and that would have to have bearings and other kinds of equipment. You'd have to have access to all those things, and so that would take up a lot of space below the deck.
Under the bridge and at the bow, the only place there's room for them, lie the beating heart of the ship, the Amethyst's engines. To get the power to the propellers, they drive electric generators. Then, cables carry the power the entire length of the ship to electric motors at the stern, which directly drive the propellers. No long drive shaft required. It's an elegant solution, but it does mean the electric motors at the stern need to be exceptionally large as well.
One of our propulsion room, we have big motors with power 4,000 kilowatts.
The most powerful electric motor in most people's house is probably in their washing machine. And each of the motors on Amethyst's propeller shafts is 5,000 times more powerful than that.
That kind of electric power gives the Amethyst the ultimate spin cycle. And to generate sufficient thrust, the propellers are 18 feet tall. But what's really clever is the mechanics hidden inside them, which means they have to be installed with extreme precision. In Taiwan, there's a rare chance to see these propellers above the water. They're installing the starboard prop on the Amethyst's sister ship, the Emerald.
This is a job that needs an engineer. It's so precise they have to sign off the measurements before we can do anything.
The blades are made from a copper, nickel, and aluminum alloy. They're designed to cut through the water with exceptional efficiency.
We can sail up to 16 knots, which is more than normal for a ship like this.
It's the fastest ship in its class. But it's what's inside the propeller shafts that makes the Amethyst's propulsion system remarkable. Each propeller has 4 blades. Normally, the system is solid. not on the Amethyst. Inside each shaft is an oil-filled hydraulic piston. When these move, they alter the angle of the blades. This means they can swivel or be feathered to change their pitch, and therefore the thrust they produce. They can also swivel into reverse, so the shaft spins the same way to go forwards or backwards. And when not needed, they have a zero drag position.
If the one propeller shall not be used, it will fold and make a minimum resistance. The ship can keep good speed with only one propeller.
Time is money, and in heavy industry, where an oil rig rents for upwards of $100,000 a day, the Amethyst has to be reliable, even if the worst happens. With 4 diesel engines and 4 electric motors, even if there are multiple breakdowns, both propellers keep turning.
This ship has the ability to automatically hold her heading in position in good weather, and she can keep doing that even if a component fails. That's why she has to have 2 motors per shaft in case one breaks.
The Amethyst's propulsion system is a triumph. The ship can cruise for 25,000 miles without needing to fill up. That's all the way around the planet. Right now, Yevgeny is anxious to meet his cargo on time. But cruising at high speed in a ship this large and heavy makes one task particularly difficult: bringing it to a stop.
It has huge amounts of momentum pushing it forward. Now, the only way really to make that stop is to have a force in the opposite direction acting upon that ship.
"8 a.m. Captain Yevgeny is motoring at full speed to the location where the Amethyst is about to load one of its most challenging cargoes yet: 2 scrap oil rigs that it will ship to Oman.
Bridge, Captain. Мы только начинаем разгоняться.
With one of the biggest ships on the oceans, even the simplest of operations, like coming to a stop, has hidden complexities. At sea, you can't just hit the brakes. This ship weighs 31,000 tons empty. Stopping is like stopping a Formula One car that's traveling at over 700,000 miles an hour.
If you have a car on land and you hit the brakes, the friction between the tires and the road will quickly bring the car to a stop. But the friction against the hull of the Amethyst is very small. And even if you turn the propellers off, that thing will keep going for a very long time.
In open water, the high-tech propellers can switch to reverse thrust while spinning in the same direction. That's 8,000 kilowatts, all used to force water backwards. It can stop the ship dead in 500 yards.
Prepare starboard anchor.
Time to drop anchor.
Please report when be ready.
Meet Alex. He's the loadmaster and has over 25 years' experience supervising some of the most complex ocean cargo operations on the planet. He's heading out to the Amethyst to plan the detailed execution of the load.
The loading can be in 3 days. But we need good weather.
Now on board, Alex studies the weather forecast with the captain. It is not looking good.
Big question mark. The direction the weather is going to, we don't like, because actually the window is closing.
The forecast become less friendly for loading operation itself, yeah. But overlook is not promising. It's not promising at all. Yeah.
They need inch-perfect positioning to load the oil rigs. If there's bad weather, it'll mean delays. If there's a storm, they won't be able to load at all. And there's one on the horizon. The question is, when will it hit? The whole mission hangs in the balance. Even in good weather, it is extremely difficult for the Amethyst to hold its position in the open sea.
A ship afloat can move in what we call 6 degrees of freedom. It can slide forward and backward, left and right, up and down, and it can also turn around each of those 3 axes, rolling, pitching, and yawing.
The Amethyst has special hinged rudders, which gives it a much smaller turning circle than many other ships of its size. In Taiwan, they're installing them on the new ship, and it needs to be done with incredible accuracy.
We need to precisely align the center line from top to bottom to make sure the rudder base is balanced when we install it.
Fitting the rudders is not easy in Taiwan's tropical high temperatures. In the heat of the day, the metal expands, which could mean the team don't put the rudder in the right place. An inch off could compromise the ship's maneuverability. So they use a simple, if inconvenient, trick.
We have to do it at night to ensure we eliminate any chance of miscalculations.
Even though the cargoes are enormous, loading them aboard the Amethyst will require extremely accurate maneuvering. Fancy rudders alone are not enough. Deep below the waterline, near the very bottom of the vessel, there are several curious shafts that traverse the ship. Inside, there are thrusters, extra side-on propellers, that can force water out of the shafts in controlled bursts.
The forces required to maintain its position precisely are just enormous. And that's why her bow and stern thrusters are huge. They can generate very large amounts of thrust very quickly when they're needed and stop again very quickly when they're not.
There are 4 thrusters, 2 at the bow and 2 at the stern.
The 4 thrusters now in operational condition, number 2 and 1 bow thrusters, and number 3 and 4 stern thrusters. So we can swing the vessel in desired direction how we need to.
With these thrusters, the Amethyst can move sideways in tiny increments, as well as forward and reverse. Like the main propellers, they can change the pitch of their blades to control the thrust they're delivering. They're part of what's called a dynamic positioning system. But although it enables incredible control of the ship, it can do nothing to control weather. Either wind speed or wave height could halt the mission.
Yeah, to load these 2 rigs, we need wind less than 10 knots. And the sea stayed less than half a meter. If it's above these limits, then we cannot load because it's not safe. We can damage the vessel, the cargo, and most important, we also can harm our crew during loading.
It's 6 p.m. off New Orleans, and Alex checks the forecast. He discovers his weather window is shrinking. The storm is heading their way, and the crew are suddenly concerned.
We have 7 squalls appears with wind speed up to 55 knots. Major swell coming from the south in the area.
The Amethyst is waiting to load 2 oil rigs with a combined weight of 25,000 tons. But overnight, the weather takes a turn for the worse.
We have 7 squalls appears with wind speed up to 55 knots.
A force 8 gale is now blowing. With gusts more than 5 times the wind speed they can safely load in, the entire operation is in jeopardy. If there's no window in this violent storm, they might have to reschedule the operation.
This is a good example of the adverse weather can change gradually just within seconds.
They resort to engine power to try to stop the Amethyst from pulling anchor.
But the anchor is holding well, and we are just confident that we are safe at the moment. So we just get ready in all respect, just in case.
After an anxious wait, the lashing rain subsides, leaving just high winds. Yevgeny needs to know how the rigs are doing. If either is in trouble, the loading will have to stop.
They are also compensating the wind effect in the area. So hopefully they are okay.
Next morning, the wind dies down. But as the crew wait for the swell to return to safe limits, new information suddenly comes in about how deep the rigs are sitting in the water. They're lower than expected. This is a crisis for the Amethyst because of the highly unusual way she's going to load the rigs. 25,000 tons of awkwardly shaped steel looks impossible to heave onto a deck. The GPO engineers had to defy shipbuilding logic.
The main deck is going underwater. We are submerging it.
The way the Amethyst will load the oil rigs is to deliberately submerge its deck beneath them and then refloat to lift them out of the water. The Amethyst is known as a semi-submersible because it only partially sinks.
There's something really impressive about seeing something just so massive submerge itself almost completely underwater and then come up again. Just the scale of these things is mind-blowing.
I find it absolutely incredible. So a ship that can sink itself in a controlled manner sort of defies science.
So how do the Amethyst designers achieve a feat that challenges the fundamentals of ship design? The answer is hidden under the deck. Below the steel lattice, there's no cargo hold, no cabins. The ship's entire hull is made of ballast tanks. When water is pumped into them, it reduces the ship's displacement, and the ship gradually begins to sink below the waterline.
Не, у тебя он идет первый крюк сверху, на этот, а второй крюк на ступеньку любую.
The Amethyst is ready to submerge, but the news that the oil rigs are sitting lower than expected in the water changes everything. The ship will have to be lowered further than planned to float the rigs over the deck. And there's a bigger problem that needs urgent attention. When submerged, guideposts welded to the deck need to be visible above the water to show the exact spot the rigs must align to.
Значит, на этот H-beam, вот тогда, как говорили, делайте прорезь в трубе, надеваете.
With the ship deeper, these guideposts will be completely invisible.
Original design guide post is 7 meters, so the guide post should be extended by 2 meters height to be visible while the floating cargo will be over the deck.
The whole operation will be called off if the crew can't modify these guideposts.
The option is to weld the special antenna up to the 2 meters high.
Extending the guideposts should enable the operation to continue. The crew have to work fast. They don't know how long the weather window will hold. Finally, the captain is satisfied. The huge deck area is now ready to receive the 2 giant cargoes, and the operation can begin. It will take about 6 hours. The hull of the Amethyst can fit 160,000 cubic yards of water, enough to fill 49 Olympic swimming pools and create a potential danger.
As the ship moved slightly in the waves, all that ballast water would slosh from one side to the other or from one end to the other, and the ship would roll over, no doubt about it. There's a very simple solution to avoiding capsizing your ship, which is to break the ship up into a large number of ballast tanks. Divide the sloshing surface up into as many pieces as you can.
The hull is split into a total of 76 ballast tanks, laid out in 3 layers. This allows the crew to regulate exactly which parts of the hull are emptied, so that the ship is always kept stable.
It's very complicated. A lot of ballasting.
Ballasting stuff.
Inside the bridge, the crew begin the submerge.
This is the main brain for the cargo operation, so this is actually the system which is vessel designed for.
The ship's 95,000 square foot deck starts to sink down 30 feet.
This is the physical process of taking the water into the designated ballast tanks, how it is calculated in order the vessel to get the positive stability all the time for the cargo operation.
By early morning, the ship's hull is successfully submerged. This is when it's at its most vulnerable.
I can't say that we are just not nervous. We are.
Partially submerged, the Amethyst waits for the first of its monumental cargoes to be floated over it. The next part of the operation is the most dangerous, bringing the cargo into physical contact with the Amethyst. This rig alone weighs 13,500 tons, so the Amethyst's crew must make sure the ship doesn't sink altogether.
All the personnel must be very vigilant all the time, and especially the guys who is operating the particular system, including the guys who is controlling this.
When the ship's ballasted down for loading, she's in a very vulnerable position. It doesn't take very much flooding before she's at serious risk of sinking.
The ship now has roughly 100,000 tons of water inside its hull. All that's stopping it plunging further are the parts above sea level. Where they break the water line is known as the water plane area.
When Amethyst is ballasted up in her transport configuration, she has a huge water plane area, and that gives her enormous stability. But when she's ballasted down in the loading configuration, her water plane is tiny.
The bridge holds up the bow of the ship, and more critically, these 2 giant towers, the stern.
These 2 towers and the forward part of the ship is actually keeping the vessel horizontal and still floating. Each of these towers have ballast tanks of about 3,370 tons.
As long as they're kept above sea level, the water plane area will be large enough to stop the ship diving to the bottom of the ocean. At last, with the weather holding, the first rig can be loaded. Alex instructs 3 tugboats to gently pull the rig towards the Amethyst. The closer they get, the higher the risk.
There's not a lot of ship above the water. She doesn't have a lot of spare buoyancy, and there are tugs and there is a heavy object moving around her. There's a very high risk of collision.
The corners of the load now need to be tied to the ship, so it can be carefully winched in to line up with the guideposts.
So the first line connected to Amethyst, starboard bow. Line number 1.
With 4 ropes connected, the rig can be pulled into position directly over the deck. They pull the rig inch by inch towards the guideposts, which mark exactly where the rig needs to be positioned.
So the rig is almost in position and the loadmaster is checking the mark against the mark on the guidepost to match each other.
It is the critical stage. When the Amethyst lifts the rig out of the water, even an inch off the mark could upset the weight distribution across the deck and destabilize the entire ship.
Additional lines are to be connected to make sure the final position is achieved.
They get it close, but not close enough. One final effort is all it needs.
Final position is in progress now. So the marker is across the marker on the guidepost, and we consider it is in position and start ballasting now.
In order to re-emerge from under the water, it has to shift out 100,000 tons of water from its tanks. It has to do so quickly, which is pretty amazing.
The ship is now ready to lift itself and 13,500 tons of oil rig right out of the water. It's the moment of truth. In the Gulf of Mexico, the Amethyst is about to start the final and most hazardous stage of the loading operation. The rig is now in place over the submerged deck. They can start bringing the ship up. Everybody's tense. The 13,500-ton rig is locked in position, but until it makes contact with the ship, it's still floating and unpredictable.
Because she's vulnerable for the whole process that she's ballasted down, Amethyst needs to move thousands and thousands of tons of water.
Pumps with high-speed impeller blades use centrifugal force to fling water out of the tanks at an incredible rate of over 4 million gallons per hour. Instead of days, they can be emptied in 7 hours.
Pumps are big in order to have a bigger capacity. It is a bit noisy here.
As the ship starts to rise, when deck and rig meet, it's crunch time.
So a lot of factors can go wrong, and we should be ready for any of this. We are trying to do this, and until now we are managing that.
One of the riskiest points in the whole operation is as the ship lifts up and makes contact with the load. We have to be sure the load's in exactly the right place.
The pumps are so powerful, the sudden buoyancy has to be tightly controlled. Right now, if anything goes wrong, it will be a catastrophe.
If there's a problem with the ballasting system and the ship doesn't come up exactly as she was meant to, that could cause the ship to lose stability. That could result in her capsizing.
But the Amethyst can shift her own weight around to keep her balance. The pumps don't just move the water out of the tanks and back into the sea. They can also move water around the ship. However the load is sitting, Amethyst can shift her center of gravity to remain stable.
As it lifts up these giant oil rigs, it needs to be careful to keep the center of the weight in the center of the vessel. And so if the oil rigs are slightly off-center, slightly further forward or left or right, it can compensate by moving the water from one tank to another.
The ship keeps rising out of the water. Success. The Amethyst has loaded the first rig.
So we are safe.
The next day, the team need to repeat the process to get the second rig onto the deck. As the ship rises once more, the ballast team keep careful watch. Both rigs are out of the water and in the right place. Now the crew can weld them securely onto the deck before their long journey to Oman. At last, the Amethyst and her incredible 25,000-ton cargo are ready to set sail for the other side of the world. It's a job almost no other ship on Earth could do.
We consider that the loading operation has been completed.
From her incredible super strong deck to her super powerful propulsion system, from inch perfect positioning to her complex multi-tank ballast arrangement, she's one of heavy industry's greatest superstructures.
Amethyst is remarkable because they put all of these different technologies together to give a heavy lift ship that can do its job just about as perfectly as you can imagine.
The International Space Station is the ultimate extreme home.
Space is an environment where human beings were not meant to live.
The most expensive structure humans have ever built. Here, in the most inhospitable environment known to man.
The only reason we can go there is by taking technology to provide us with everything that we need in order to stay alive.
With no air, food, or water, 250 miles above the Earth, it's an epic engineering challenge.
We as engineers are having to figure out how to make systems that provide all those functions that Earth provides in a tiny little can.
To reveal how the engineers pulled it off, we're going to take it apart and uncover what's going on inside. How the International Space Station and its superstructure secrets will help our species reach other planets and beyond. Costing up to an astonishing $150 billion. This is an unprecedented home.
The ISS is an extraordinary feat of engineering because not only do you have to make this big environment that people can live in, which, you know, is non-trivial to do on Earth. You have to do it in space.
It comprises millions of high-tech components. There are 16 pressurized modules with living quarters, sleeping bays, an observation deck, and 6 science labs, all connected via airtight tunnels. There's plenty of parking for visitors, including spots reserved for Russian Soyuz capsules, and the ISS's lifeboats, which are on permanent standby in case of emergency. Unlike any other structure, the ISS has to provide everything its astronauts need. If it fails, they die.
A human being can only survive for 3 weeks without food, 3 days without water, and 3 minutes without air.
For humanity to successfully venture well away from Earth, astronauts will need to be self-sufficient. If the ISS can solve the challenges, it will prove humans can truly live in space. But before anyone can take up residence, the engineers behind the ISS had to get it into space. And it weighs a colossal 460 tons, the same as about 300 cars.
It would be great if we could just build the International Space Station on the Earth and then just blast it into space.
You couldn't just fly the whole thing up there in one shot. You had to take a piece at a time and assemble it together like Lego.
The ISS began life as just 2 modules that had to be connected in space, one built by America and the other by Russia.
The first flight actually launched in November of 1998. Hadn't been that long since the end of communism in Russia, and here we were building a joint Russian-US space station. So just the political milestone that represented was pretty significant.
After the intense competition of the space race, it's suddenly all about collaboration. The orbiting Russian module is known as Zarya, which means sunrise. Next, the first American module, known as Unity, sets off inside the cargo bay of Space Shuttle Endeavour.
Liftoff of the Space Shuttle Endeavour.
Unity is now chasing Zarya through space at more than 17,000 miles per hour. 2 modules from 2 superpowers are about to dock.
First thing we have to do is to open up the payload bay doors.
Can you imagine how important it is for these 2 modules to mate?
Unfortunately, before both modules were launched, engineers spotted a problem.
Not all the pieces got to be integrated on the ground before they were launched.
Neither Zarya nor Unity were originally designed for the ISS. Their docking systems wouldn't fit together.
The Russian hatches are all round, and our hatches are all square.
I mean, this is fundamental to the International Space Station, and what you have are 2 things that don't mate.
And so, what do? Well, you make an Adapto-Lego block connector thing.
The L-shaped Lego thing they came up with is called the Pressurized Mating Adapter, or PMA. Not only does this accommodate the different shaped hatches, it also has a precision-engineered docking ring for grabbing hold of another module and perfectly aligning it. Vital if a reliable airlock is to be made. This is the moment of truth. Latches on the inside of the docking ring finally make the connection and pull the modules together.
Houston Endeavour, we have capture of Zarya.
The International Space Station is born.
It was amazing. I mean, here we are. We got airborne. We had Unity in the bay. And when we left a functioning space station ready for the next module to come up.
In the 20 years that follow, engineers from all around the world join the project, building their own space laboratories and bigger living quarters. But every one of the modules was constructed on Earth, and it takes a supreme international effort to launch them all successfully into space.
It took a long time to build Space Station. We have to fly everything up, we have to connect all the modules, put them together. So that took over 40 missions. Modules came from all over the world. We have the US modules from NASA, we have the Russian modules, we have the Japanese modules and the European module, you name it.
And it costs around $10,000 to send every pound of weight up here from Earth.
So right now, we're in the Japanese laboratory. It's one laboratory out of many here on the International Space Station. This is Columbus, the European module. It has science experiments all over. You could see it looks a little bit crowded. Here we are in the US laboratory. Again, this is a laboratory with science experiments on all of the walls here. So we're going into the Russian segment. Be ready. You don't need a passport either. And what's cool about this module, it is actually the very first piece of the space station that came up in 1998.
It's been occupied continuously ever since then. So if you think for 18 years, there has always been a human presence in space.
Today, the ISS is enormous. By far the largest space station ever created.
It's actually big enough if you have a good pair of binoculars, and when it's flying over, right overhead, you can actually see it. Normally you look at a satellite and it's just a little dot, but the ISS is big enough that you can actually see it as an extended object.
It's so vast, in fact, that it would dwarf Times Square. At an astonishing 357 by 240 feet, it has more living space than a 5-bedroom home. But the larger the International Space Station becomes, the larger a very obvious issue becomes, too. Air. In space, there is none.
It doesn't provide a life support system for us, air, oxygen. And so if we have a home in space, we need to provide all of that.
The average adult breathes close to 4,000 gallons of air per day. With a crew that can be up to 9, the ISS must supply a huge amount of it. And it's not coming from outside those windows. Cruising outside the Earth's atmosphere, the International Space Station has to provide everything the astronauts need to live. And breathable air is first on the list.
Their very survival really depends on the things that we provide them. And you're also having to deal with the fact that at any point in time, if one of your system fails, you have a very limited amount of time to either get something from Earth or to get back to Earth as quickly as you can.
In a crisis, an emergency supply of oxygen can be sent up by rocket. With technological advances, spacecraft can now rendezvous with the ISS in 6 hours, if everything goes as planned. But even when a cargo delivery is successful, there's a price to pay. The cost of each mission is colossal, almost $200 million.
It's expensive to bring a kilogram of anything up to the space station. And to spend all that money just to bring up water and oxygen would be an incredible waste.
The ISS needs to make its own air.
The oxygen on the ISS can come from a delivery from Earth, and then they're stored in tanks. But the ISS is also capable of generating oxygen on board.
On Earth, we take air for granted. In space, each astronaut must be supplied with 1.85 pounds of oxygen per day, 365 days a year, to avoid suffocating. In the very heart of the ISS is an unassuming machine about the size of a trash can. It's this that holds the secret to keeping astronauts alive. Incredibly, it generates oxygen from nothing more than water.
So what happens is you have some water, you feed some electricity through that water, and the electricity will split that water into hydrogen and oxygen.
The oxygen comes off as bubbles at the positive electrode, the hydrogen at the negative. But again, being in space turns something that's straightforward on Earth into a major engineering challenge. The bubbles of gas won't come out of the water.
In your high school chemistry lab, the gas just bubbles up to the surface because the gas is lighter than the water, and therefore it goes up. Gas is not lighter than liquid in space because gas doesn't have any weight and liquid doesn't have any weight. So you produce gas bubbles and they just sit there. And what we generally do is we centrifuge it. So you spin it all around, and the liquid, being denser, it doesn't weigh anymore, but it still has mass. So it's denser, and it goes to the outside, and you can then separate the liquid from the gas.
The hydrogen gets thrown away, gets pumped into space, and the oxygen is used for the ISS air supply.
There's enough capacity on board to generate 5 to 20 pounds of oxygen a day. More than enough for the crew. In the extreme environment of space, making air is just the first challenge. The ISS has to keep it, but it's under constant threat of a breach in its hull.
There is so much space junk up there now.
There's the potential for it to puncture the outer wall of space station.
I was taking pictures out one of the windows, and it was a nice clear window. I came back sometime later to take another picture, and there was a great big ding in the window, about a 5/8 of an inch in diameter from a micrometeorite impact. And we had to take pictures, close-up pictures, send it down to the ground, and it had to be analyzed to see whether it was going to be a threat when we entered.
If you pop a hole in space station, the atmosphere is going to leave very, very quickly.
No atmosphere means no oxygen, and the consequences of that are obvious. So how does the ISS deal with the threat of colliding with meteorites? The International Space Station is the largest man-made object that's ever orbited the Earth. And it's racing around our planet at 5 miles a second. But on board, that's hard to appreciate.
How do we sense speed if you're in a car, for instance? You know, you have the road noise, you have the wind going by, you have billboards or trees going by your window. None of that exists in space. The only way you get a visceral sense of how fast I was going is, you know, you're going over the Pacific Ocean, and then 10 minutes later you fly over New York, and then 10 minutes after that you're flying over London.
If the ISS was orbiting closer to Earth, we'd all see how terrifying its speed is. It would cross the US from coast to coast in just 10 minutes, lapping the Earth more than 5,500 times a year.
But it's actually traveling at 26,000 kilometers per hour, or 17,500 miles per hour. So definitely be breaking the speed limit, right?
Speed on Earth can be incredibly dangerous, but in space, at the velocity the ISS hurdles, the consequences of a collision can be off the scale catastrophic.
Space debris is going by you at about 5 miles a second, so if there's a big piece of debris that happens to have your number on it, it's moving so fast you'd never see it.
March 23, 2012, Mission Control radios the crew.
And how about relative velocity? Any idea? Checking.
Something is heading straight for the space station.
The time of closest approach of this fragment of space debris is 11 minutes from now.
No one knows how big this object is.
Well, you do what you're trained to do, and even though you got woken up in the wee hours of the morning, you know what the reason is.
The crew must prepare the space station for impact.
Can you see? Yeah. Yeah.
You go through and you close every single hatch on station, which takes about 45 minutes.
Yeah. And from which direction? Yeah, we don't know.
The hatches can withstand a sudden loss of pressure that would come from the hull being breached.
Coming up on the 6-minute mark.
If there is a puncture, any loss of air could lead to a serious emergency.
Coming up on the 3-minute mark until the time of closest approach.
The crew takes no chances. They head for the escape vehicles.
We floated into our Soyuz spacecraft with initial preparations for undocking if space station were to be hit.
About 1 minute from PPA.
And you just kind of hunker down and hope it doesn't hit you, and you just sit there and wait.
Looks like that's it.
Fortunately, this time it's a near miss. But the ISS cannot rely on luck.
The International Space Station is designed to work in the low Earth orbit, which is full of space debris.
A lot of space junk is human-made. You know, they are things that we have put up there, satellites largely.
NASA has identified more than 500,000 orbiting objects that could pose a risk to the integrity of the space station's hull.
Luckily, most of the stuff that's big enough to hurt us we can track. There are a few objects up there which are too small really to be tracked well, but they're big enough to do damage.
The ISS is constantly bombarded. Most of the debris is tiny, but even a half-inch fleck of paint could inflict the same damage as a motorcycle crashing at 60 miles an hour. To be a viable home, the ISS has to be able to take the hit without losing all its air.
The ISS basically has a bulletproof vest. So just like a bulletproof vest, which has different layers of Kevlar that can rip as a bullet enters it, the ISS has different layers in its outer skin.
The space station's skin is known as Whipple shield. The outer wall is made from a thin sheet of aluminum, less than 1/10 of an inch thick. Beyond that is a blanket of woven material and a further thin wall of aluminum. It seems too delicate to protect the ISS from a direct hit.
It turns out that a solid piece of metal does not offer as much protective power as if you cut that metal into very thin sheets, spread them out a little bit.
When there's an impact with a high-speed micrometeoroid, it hits the outer wall of the ISS and pulverizes. Some fragments pass through the first layer of aluminum, which disperses some of the energy. Then there are layers of Kevlar and Nextel, a ceramic fiber that's stronger than some metals. As the fragments hit this blanket, they break up even more and don't have enough energy to penetrate the hull.
It's kind of counterintuitive when you think about it, you know, that a whole bunch of sheets of aluminum foil could somehow give you more protection than putting them all together. But that's the way it is in space.
The Whipple shield has protected the space station from micrometeoroids for over 20 years. But it's ineffective against anything larger. If a large object on a potential collision course is identified, the only option is to move the whole ISS out of its way.
Space Command monitors most of the space debris that is out in orbit. They notify our mission control here at NASA. We look at that and we have a green zone, a yellow zone, a red zone.
Objects that fall within the red zone have a 1 in 10,000 chance of hitting the ISS. Too dangerous to ignore.
If we think that something is coming within the red zone, the space station can adjust its orbit and give itself a little boost to get out of the way.
Small thrusters change the ISS's trajectory, but using them is expensive.
Now these thrusters, you can think of them almost like tiny rockets, and those rockets are using propellant, and that propellant isn't infinite.
It all has to be sent up from Earth at a cost of $10,000 per pound of propellant. This brings engineers face to face with the greatest challenge of all: how to reduce the station's reliance on Earth. The ISS can't be self-sufficient if it relies on thrusters to move. But a clever trick hidden at its center means it doesn't have to. The International Space Station has a problem. It orbits the Earth every 90 minutes and has to be regularly reoriented. Using thrusters is one option, but that uses up precious propellant.
With the space station, if here's the Earth, we want to keep the station, usually, I mean, there are sometimes exceptions, but usually you want to keep the station in the same relative orientation towards the Earth so that the cupola is looking down at the Earth. And in order to do that, of course, the space station is going to be rotating once every orbit around the Earth.
What the ISS needs is a way to move that doesn't use propellant.
The solution for keeping the ISS in the right altitude and also on track in direction is to use gyroscopes.
This is one of the ISS's most innovative secrets. At the center of the sprawling space lab, there's a quartet of small casings, each about the size of a small cupboard. They're known as control moment gyroscopes, or CMGs. But how can they move a beast the size of a football field?
They're really, really clever in that you can change the attitude of station without firing any thrusters.
The 4 CMGs are mounted on a truss near the very core of the ISS. Inside each casing is a flywheel, spinning at 6,600 RPM. The flywheels create a lot of angular momentum, and simply by changing the RPM, or tilting the plane they spin in, they transfer that momentum to the ISS, and the whole thing moves.
If I were sitting here in a chair and I had a gyroscope spinning around in this direction, and all of a sudden I put a brake on and slowed down the gyroscope, the chair would start to spin around. You know, I would slow the gyroscope around and then, woo, I would do a big spin because that angular momentum has to be conserved.
So these 4 control moment gyroscopes can move the whole of the International Space Station, and there is not one single drop of propellant used in order to make that movement.
But they do use electricity, as does just about every piece of equipment on board. To supply the ISS's total power requirement, a whopping 75 to 90 kilowatts, engineers cleverly exploit the ferocious power of the sun. The station generates all its electricity for free.
The solar panels on the space station are absolutely essential because they provide all of the power that the station needs.
The panels have to be enormous, which would have made them impossible to transport had NASA engineers not come up with a genius way to get them into space.
What's really impressive about the solar panels, not least their size, you know, around ½ an acre per array, but the fact that they are actually folded, and then once they're in space, they were able to be unfolded. Now that's an amazing thing to do in space.
Together, they can generate 120 kilowatts, ample for all the ISS's needs, and the equivalent of powering 40 homes.
In order to maximize the power you're getting, you have to keep this solar panels continually pointed at the sun, which means as the station is moving, the panels have to turn.
And so we have gimbals. If there's a solar panel, we can gimbal this direction, and then we can gimbal this direction.
One of the ISS's greatest engineering triumphs, it's been generating its own power for over 177,000 hours and counting. That enables round-the-clock air conditioning, fundamental to astronaut survival.
This cannot go down. It's not like a power cut in our homes where, you know, we can get a torch or light a candle or something. If this goes down, astronauts will die.
When the ISS enters the shadow behind the Earth, the temperature can drop to below anything ever experienced on our planet. Without the protective cocoon of the space station, the ferocious cold would kill astronauts in a matter of moments. Conversely, when in sunlight, the temperature can soar.
Temperature and managing temperature on the ISS is very important. If you imagine the extreme temperatures that you can get on the ISS if you're facing the sun or not, could be plus 250 degrees or minus 250 degrees.
So you have these huge temperature extremes simply because of being sunlit or being in the shade. And it's something that you have to keep in mind when you're doing your engineering.
Of these threats, overheating is the hardest to manage.
With lots of people and electronics inside a spacecraft, you tend to generate more heat than you know what to do with. And so the problem in general, at least in Earth orbit, is that you've got to get rid of heat.
If heat built up uncontrollably inside the ISS, it would become a deadly incinerator. So cooling the station is a crucial priority.
Standard ways of cooling that we're used to on Earth don't work. Convection does not work. Conduction does not work.
Conventional aircon would be ineffective. Scientists had to come up with a cooling system for radiating heat away from the ISS. It needs to be liquid-based, but there's a dilemma.
Ideally, what you'd like to be able to do is just put it through a water cooling system and then get rid of that excess heat. If they tried to get rid of that excess heat using water, the water would just freeze as soon as it went outside into space.
Water is not the solution. Curiously, gallons of a deadly poison is. Hidden inside the hull, there's an intricate network of pipes picking up the heat. But they do carry water. The secret is, the water goes through heat exchangers, where ammonia-carrying pipes take the heat outside the ISS. Huge radiators finally dissipate it into space. Ammonia is used because, unlike water, it doesn't freeze until minus 107 degrees Fahrenheit. It remains liquid and flows through the radiators, even when the ISS is behind the Earth.
Ammonia is used as a heat rejection system because it is one of the best thermodynamic fluids to use as a heat rejection fluid. Unfortunately, it's incredibly toxic and kills human beings on contact.
In May 2013, for reasons unknown, ammonia is spotted leaking out of one of the cooling pipes. There is no alternative but for astronauts to climb outside the ISS to fix it.
Fireflies coming off our space station.
The International Space Station has a network of vital cooling pipes that are filled with ammonia, a substance so toxic it can kill.
Now, there was a time in 2013 when Chris Hadfield and his crew spotted a leak from the ammonia pipes, and they had to react very, very quickly to stop that leak.
The leak appears near one of the solar panels. There's only one viable response to this critical emergency. Astronauts Chris Cassidy and Tom Marshburn must exit the ISS and investigate.
Sunlight, I am putting my visor down.
They discover ammonia spewing out of what they think is a pump.
Fireflies coming off our space station.
If they can't stop the flow, they might have to evacuate the space station.
You're going to monitor for an ammonia leak. If some reason a flowing leak is observed, immediately stop turning.
The pair attempt to replace the suspect pump. Hard work in cumbersome spacesuits. And they must avoid contact with the potential lethal ammonia.
Be careful not to put your hand inside that window, and also the seals on the FQDC are no touch.
No touch on the seals, don't penetrate the window, copy all.
5.5 grueling hours later, the astronauts return to the ISS unharmed.
That's affirmative. The ammonia valve is closed.
It was fortunate that the leak wasn't water, because along with oxygen, water is one of the precious commodities people cannot live without. It's so precious, in fact, that inventing equipment to recycle it was one of the space station engineers' highest priorities.
It's so important that we recycle as much of the water on the ISS as possible. And that includes things just like the water in the air.
The end goal is for the spacecraft to recycle 100% of their onboard water. That's far from straightforward, because much of it starts off inside the astronauts.
That water vapor comes from the individuals. As you breathe, you exercise, you sweat, and then it comes off of the surface. So that's the water vapor that gets out into the air, and we're constantly ventilating the air through the module.
Water vapor from the air is collected in a condenser. Every droplet is valuable. Nothing is wasted. Even urine is recycled.
Let's say you're up here on ISS and you need to go to the restroom. You want to come to this cabin, and the first thing you want to do is grab this piece of equipment and turn this rotary switch 90 degrees to the open position. What that does is it turns on a fan, which creates a suction effect in this hose, so that you can use this yellow element for your number one.
After an astronaut uses the unusual facility, water products flow to the life support rack, where filters get to work. The start of a sophisticated process.
So the way space station turns urine into water is that the urine goes into what we call the urine processing assembly.
There are a number of stages. The first is treating the urine to prevent buildup of bacteria or other dangerous microbes.
That urine that we collect from the crew, we have to add chemicals to it in order to process it. Raw urine in and of itself would be a problem, because over time it becomes rancid, and that's definitely a bad situation on the space station. So that's why this is a dark fluid instead of what you would normally think of as urine.
Clearly, that is not drinkable. It needs to be distilled, where pure water is boiled off to leave the toxic waste products behind.
And then it goes through another cleaning process. There's lots of filters. And then some of the water is made available for drinking. And that's why we have the expression that the water recycling system is coffee to coffee. You can think about that.
The water that gets to the crew now is effectively cleaner than any water that we drink here on Earth. Even that nice bottled water that everybody likes so much, it's cleaner than that. So this is the end point in the process.
It tastes really good.
In water recycling, we are really trying to get to the point where we can recycle up to 90 or 95% of the water on the space station, which is really vital not only for going someplace like Mars, but also has consequences here on Earth.
Recreating the conditions that support life on Earth is one of the pillars of the ISS. but much of its equipment is still operated by Mission Control in Houston. The ISS will have to break free from that if we're ever going to conquer deep space.
We're going to have you go to the ticker shroud removal.
Okay, copy.
The International Space Station provides its own life support, but it's partly controlled from Earth.
Go off a bit. Off a bit. There it is. Yep, I felt it.
Okay, Swanee, what do you want for...
Our flight controllers on the ground can control the robot arm and move that from the ground.
That requires constant radio communication. A major challenge because radio waves can't penetrate the Earth, and the ISS is often behind it.
What a beautiful piece of hardware.
We can have significant loss of signal with the space station. We're talking on the order of maybe 12 to maybe 40 minutes, maybe a little bit longer.
In the early Apollo space missions, they tried to fix the problem with a fleet of jets that bounced radio signals between each other, ground bases, and space capsules. But it was expensive and unreliable. The ISS uses a more sophisticated system.
There are various assets that we're able to use to communicate with the International Space Station. So one are via satellites.
A network of high-orbit satellites relay radio data between the ISS and ground bases in several countries across the globe.
And Mission Control, we're looking at various video feeds. So we have the first board over here, we call it the 6-pack. And the International Space Station allows, at a minimum, 6 downlink video channels. And then we can be following the crew, what they're doing during their day.
Station Houston on Space to Ground 2, you have a go for Step 6, Ingressing Dragon.
Copy that.
The live links are so reliable and fast, there is now less than a second's delay when astronauts communicate with Earth.
Hi, Dad. Hi, Dad. How are you? Hey, Rob. Hey, bud. How's it going?
Currently looking at what we call the world map, it would show that the International Space Station is currently about to start swinging north of Antarctica. Another cool feature about the world map that we keep in front of the control room is the fact when other missions go and launch, we'll also see those vehicles where they are relative to the International Space Station.
3, 2, 1. Engine ignition, liftoff of the Falcon 9 rocket.
The ISS may still be in our local space neighborhood with the luxury of near-instant communications. But it's also our first stepping stone to reaching other planets and beyond.
Science for today and for deep space exploration tomorrow.
Inside this rocket is an experimental new module known as BEAM.
The first human-rated expandable structure to be flown in space, now attached to the International Space Station.
After docking with the ISS, astronauts test its unique feature. It blows up like a balloon.
It's an inflatable module that's attached to the space station. It's kind of unique in that the fact it is inflatable.
It looks great. It looks pristine.
Pressurized air pumped into the extraordinary new module transforms it into a rigid structure.
One of the unique things about BEAM is that because it is collapsible, you don't need as large of a launch vehicle to carry it. Also potentially less weight because of less structure with it.
If successful, the ISS's brand new living quarters could lead to much bigger space structures. Ultimately, the plan is to house far more than the 220 people that have so far been to the space station.
We've been very privileged. We've seen our home planet from a very different perspective. First of all, it's incredibly beautiful. I mean, you look at the thin blue line that's our atmosphere, you look at the aurora, you look at thunderstorms, you look at the beautiful oceans. When you start looking a little closer, there are some troubling things. You basically see the impact that humans have had on our planet, and that can be pretty scary at times.
The long game for humanity could be to stop being a one-planet species. The ISS is the first step towards that future.
In the future, we're going to have hundreds, thousands, I hope it's 10,000 of people living, working in low Earth orbit.
Research on the ISS is heavily geared towards improving life for astronauts who will travel much further than ever before.
It's phenomenal. So it really is the world's greatest laboratory.
On Space Station, a lot of the experiments that they're doing are human-based experiments in order to learn more about the human body so that we can endure a 2.5 year mission to Mars and back.
From fitness to food production, the focus is on long-term self-sufficiency for astronauts.
And we are developing the Orion capsule here, which will be launching the first manned mission in 2022.
And liftoff at dawn, the dawn of Orion, and a new era of American space exploration.
Missions in the coming years are only possible because the International Space Station has solved so many of the problems that space presents.
The future for space is bright, and it's going to be exciting.
Everybody is excited and feel like as though in this development phase you can really make a difference.
The ISS is an incredible superstructure, a piece of Earth-like habitat floating above our planet, where every component has taken breathtaking engineering. It's now a vital springboard for deep space travel that generations to come might thank us for. This tower is a pinnacle of modern engineering. It's more than half a mile high.
This has never been done at this scale before anywhere in the world.
Dubai's Burj Khalifa is the world's tallest building. Weighing in at more than 500,000 tons, the desert skyscraper contains enough steel to stretch a quarter of the way around the world. But without a revolutionary internal structure, it wouldn't even stand up.
You couldn't take what had been done in other buildings and just enlarge them. It doesn't work.
It's so daring that during construction, designers tore up their plans and upped the ambition.
We were able to go much higher than we started, and they kept on getting taller and taller.
Today, it's the tower against which all others are judged.
Every time I come here, it's like I'm actually in awe of what we did.
Much of what is incredibly innovative about the Burj Khalifa you will never see at the building itself because it's all hidden away behind the facade.
The only way to find out how this superstructure became reality is to take it apart and uncover its engineering secrets. The Burj Khalifa is an unbelievable 2,717 feet tall. This mega tower was designed as the centerpiece for a new global city.
The development of the UAE was reliant on its oil wealth. But as this diminishes, they need to future-proof themselves. And so what they're doing is making the area a destination to visit for entirely different reasons. Who wouldn't want to say that they visited the tallest building in the world?
Dubai's central location makes it an ideal spot to attract tourists from both Europe and Asia. But it's also one of the most unsuitable places on Earth to build skyscrapers, thanks to the unforgiving conditions of the Arabian desert.
Dubai is one of the toughest places to build anything, let alone the tallest building in the world. It's extremely hot and it's extremely dry.
Back in 2003, when the Burj was first dreamt up, this part of Dubai was little more than just sand. To bring this ambitious project to life, a team of the world's best engineers is assembled, led by skyscraper expert Bill Baker.
Whenever you start a project in a new location, you need to find out what are you going to be sitting on. Are you on sand? Are you on rock? Are you on clay?
When Bill and his team investigate the site for the tower, they drill hundreds of feet down into the ground. Their results could not have been worse.
What we found, what was down there was a sedimentary rock. So it's a rock. It's not like a strong limestone or granite. The rock is called calcisiltite. So to take that word apart, calcia is like seashells. So a silt means dust-like particle. So let's call it seashell dust.
The tower is in serious trouble before construction even begins.
A building of this size will weigh a huge amount and will also require extremely solid foundations. These are difficult to achieve when you're digging down into a sandy environment because there's no bedrock to lock that building into.
As time passes, the building could settle, which is to say, one part of the building starts to sink. And in that case, you have a very serious problem. Houses can settle. You can go back into a settling house and jack it up. You cannot jack up the world's tallest building and simultaneously one of the world's heaviest buildings.
Without solid foundations, buildings can't support themselves. Italy's famous Leaning Tower of Pisa was built on top of weak sandy soil with measly 10-foot foundations. It didn't stand a chance. Chicago's Monadnock building sits atop swampy, soft ground. It's sunk by 21 inches since it was built in 1891. And in less than a decade, the Millennium Tower in San Francisco has sunk by 18 inches. And worse still, it's tilting northwest by more than a foot, cracking dangerously.
The Burj Khalifa is incredibly heavy. The base of the building actually carries the weight of the building itself, which means that the bottom is carrying all the weight of the entire building above it. This has never been done at this scale before anywhere in the world.
Once complete, it will weigh more than 500,000 tons. With no solid bedrock to anchor it into, Bill and his team are forced to rethink. The solution they come up with is ingenious. The Burj sits atop a gigantic 12 feet of concrete, which is sunk 24 feet below the surface. It covers a massive 80,000 square feet, the same as 28.5 tennis courts. It's known as a raft foundation because it floats in the soft ground, cleverly spreading the colossal weight of the tower across a large surface area.
Now, if you think about it, if you're out in the summer walking on grass and you've got stiletto heels on, we all know that the heels are going to dig straight in and you kind of want to fall over backwards. But if you had a flat trainer on instead, that doesn't happen. And the reason is that your weight is being nicely distributed and spread across a larger area, so the pressure is lower. Whereas in a stiletto, there's lots of weight on a very concentrated point.
The raft foundation spreads the weight incredibly well, but the raft itself has to be kept in position. Any shift sideways and the tower could start to lift and eventually topple. The raft is secured by 194 concrete piles. Each are 5 feet in diameter and reach more than 164 feet down through the soft ground. But unlike traditional piles, they never reach solid ground. Instead, they rely on friction to hold them in place.
Friction is a really surprisingly strong force. Although any one of those foundations, which are just going into sand, isn't able to support a huge amount of force being exerted on it, if you have enough of those piles, which have a tiny bit of friction on each one, then collectively they can support the enormous weight of this building.
Despite the desert's best efforts to thwart them, Bill and his team lay some truly remarkable foundations.
The building settled very little, somewhere between 40 and 50 millimeters, which is a little less than 2 inches. So, my thumb is 1 inch thick, okay? And so the building settled a little bit less than 2 thumbs, to give you an idea of how much this building went down. So it's a very good foundation.
The engineers have overcome the problem of the unstable desert ground, but they still have more than half a mile to go, vertically. Strong foundations aren't enough on their own to keep the world's tallest building standing. Just as important are the load-bearing solutions hidden inside the tower itself.
We think of skyscrapers as buildings built out of a metal frame with a glass curtain wall hanging from it. But the Burj Khalifa is actually site-cast concrete.
It's the ideal material to construct the Burj Khalifa. Dubai is known for its well-established concrete industry. Concrete is also incredibly quick to build with, thanks to the use of a mold called a jump form.
The jump form is made up of a series of walls that are generally made from wood, but then they've got lots of hydraulic legs and arms which basically prop it up to create a mold into which you then pour the liquid concrete. Then the concrete can harden, it can set.
Once the concrete has set, the mold is jacked up to the next level, and the process begins again.
With a traditional formwork system, you'll probably be looking at 6 or 7 days to do one story. On the Burj, we were typically operating on 3 days of floor, and we even achieved 2.5 days at times.
Speed is crucial. Even amidst concerns about low pay and poor conditions for the migrant workforce, every day of construction costs hundreds of thousands of dollars. The tower shoots up at a phenomenal speed. But as it gets taller, construction becomes more and more difficult.
Pumping concrete to a height of 610 meters, well, it just hadn't been done before. It hadn't needed to be done.
But it needs to be done now, and quickly. Constructing the world's tallest building isn't easy. Every stage and every process must be supersized.
One of the challenges is just getting the construction materials up to the height where they're required. So right on ground level, but imagine you're trying to pump concrete up dozens of stories.
It takes about a minute to pump concrete up 50 feet. So to get to the upper levels of the Burj Khalifa, it will be in the pipes for more than half an hour, which is a big problem.
It can start to harden, and that would be really, really bad for the pumps. It would essentially cause the pumps to fail.
If the pumps fail, construction will grind to a halt. To prevent a catastrophe, engineers must create an entirely new type of concrete.
So they can add what we call admixtures, so they're little chemicals that we mix into the concrete to change its properties to make sure that the concrete you're using is liquid enough and kind of plastic enough that it can actually be pumped to those heights before it hardens.
After weeks of testing, the perfect mix is made, but it still isn't enough to get the concrete where it's needed. To avoid it hardening too quickly in the searing desert heat, the concrete must be made with ice and only pumped at night. The most powerful pumps on Earth are brought to Dubai to do the heavy lifting.
They use this amazing pump called a Putzmeister, a great name for a concrete pump. Putzmeister was able to actually, in one single lift, pump the concrete from the base of the building all the way up to 600 meters.
Pumping concrete to a height of nearly 2,000 feet sets a new world record, the first of many for the Burj Khalifa. At the center now stands a hexagonal concrete core. Inside the concrete are enough steel reinforcement bars to reach a quarter of the way around the planet. But the Burj's unparalleled height once again presents a problem.
This concrete shaft core by itself is too slender to go to such great heights.
Without a helping hand, it could not stand up.
You couldn't take what had been done in other buildings and just enlarge them, okay? Just like you can't take a small animal and make them the size of an elephant. You know, it doesn't work. We had to come up with a different structural system, with a different solution, a different system.
Bill's new system is inspired by centuries-old cathedrals, where the main building is supported by buttresses. The Burj Khalifa has 3 such buttresses, which wrap around the central core. Their ingenious positioning helps them dissipate the loading forces away from the core and spread them over the full area of the foundation slab. It's the first time this configuration has ever been used on a skyscraper.
If the huge load coming down the center of the tower wasn't spread out in the way that it is, the amount of stress going onto the ground would have been much, much higher.
With the supportive buttresses taking shape, and with the problem of the concrete solved, the Burj flies ever higher. But the taller it gets, the more dangerous it becomes for the workers.
I can't prepare.
Steel cages are used to transport people to the highest levels. And as soon as a level is complete, a fence is erected along the edge. Tragically, at least 3 contractors die during construction. Today, workers still have to brave the extreme heights to do their jobs.
We are at level 109. We are above the Armani entrance. We have a task of cleaning this part of the facade.
It takes 3 months to wash the building from top to bottom, and it's all done by hand.
We have 36 Spider-Man that goes outside to clean our windows. And honestly, you need to have nerves of steel to be able to go outside.
Thankfully for these men, climbing extraordinary heights is in their blood, because they have come all the way from Nepal.
Where else other than the Nepal, where we have the Himalayas, to bring our rope access technicians from? Every time I meet with them and I'll tell them, how did you feel today? Just another day, sir, you know? Just another day.
Each man is attached to the building by 3 ropes, and the conditions are carefully monitored.
Today it is extremely windy. We are now at roughly 19 knots, and we normally cease our operation at 12.
With the wind picking up, the men are in real danger. Keeping the world's tallest building, the Burj Khalifa, looking its best is a full-time job. Made all the harder by the extreme height and challenging conditions.
21, 22, 1, 2, 1, 2.
22 knots is over 25 miles per hour, strong enough to send the ropes and equipment flying into the glass.
It is extremely windy. We have to stop now. We're calling them back in.
The wind isn't just a danger for the workers. It could also shake the entire building apart, were it not for some very clever engineering. By 2007, 3 years after breaking ground, the Burj Khalifa is well on its way to becoming the tallest building in the world. It's already taller than the Empire State Building, and there are tens of stories to go. But the taller it gets, the more danger it's in. Here in the Arabian desert, epic sandstorms are a constant threat. The high winds bring with them thick clouds of red sand, causing havoc on the roads and shutting the airports. Such apocalyptic storms are rare, but in summer, Dubai is often hit by strong northwesterly winds. They can reach speeds of more than 50 miles per hour and pose a serious danger to the Burj.
Wind is going to be a problem for any tall building, but when a building is this tall, it's an even bigger issue.
The classic shape of a skyscraper is a huge, well, basically rectangular face, and that is an absolute disaster from an aerodynamic perspective.
When the wind pushes against any building that's of a constant dimension from top to bottom, it'll create these things called vortices, little swirls in the air that come off one side than the other.
As those vortices get generated, they create low pressure regions which push on the building or suck on the building. And if you don't design the building right, those forces can cause the building to sway and shake.
In 1940, wind hitting the flat face of the Tacoma Narrows suspension bridge causes vortex shedding, contributing to its spectacular downfall, just months after it opened. And in 1965, high winds destroy 3 cooling towers at a power plant in England. To prevent a similar disaster in Dubai, Chief Engineer Bill Baker tested the mega tower's design extensively before any building work began.
So we went in the wind tunnel, we got the test data, and the data was not good at all. The building was moving too much, the forces were too large.
The team had to do something to reduce the sway.
Tall buildings have, for much of the 20th century, used a very basic mechanism to deal with building sway, which is you have a very tall weight hoisted to the top of the building that sits in a kind of sling and is designed to counterbalance any movement of the building.
It's called a mass damper and is the system used by Taipei 101, the previous holder of the tallest building in the world.
So if the building begins to sway a little bit too much to the east, the counterbalance will move to the west in order to help the building stay righted. It doesn't keep the building from swaying, but it keeps it from swaying too much.
Taipei 101's damper works well. In 2015, it swung into action during a typhoon that brought with it winds of 115 miles per hour. But its protection comes at a price.
The mass damper in the Taipei 101 building takes up 6 floors. They simply didn't want to waste that kind of space in the Burj Khalifa, so they've cleverly designed it to avoid the need.
Bill came up with an unconventional idea that both tamed the forces of the wind and removed the need for a giant damper in one fell swoop.
The way we addressed the problem here was to reduce the forces. What we did is we reshaped the building.
When you look at the Burj, the first thing you see is not a traditionally shaped skyscraper. It's got a very unusual cross-section. And as you move up the Burj, that cross-section changes. It rotates, it changes size.
The tower takes its shape from a desert lily with 3 petals, giving it a unique wide-shaped footprint. It gets narrower as it rises, and it spirals around, so no single face runs its entire height.
It's almost like lots of different height skyscrapers all fused together.
The result is that when the wind hits the Burj, it reacts with different levels in different ways. And that means the vortices are different at different heights. So instead of having one massive coherent vortex that can exert a huge force, you have lots of much smaller ones.
And what that means is that these vortices can't really ever get a strong grip on the building and do damage to it.
When Bill returned to the wind tunnel, the results were shocking. And the final height of the Burj Khalifa was drastically revised. This observation deck on floor 148 of the Burj Khalifa is more than 1,800 feet high. Hundreds of people flock here every day, drawn by the building's jaw-dropping height. But this mega skyscraper was never supposed to be this tall.
To be the tallest, this was not our aim at the beginning. The aim was doing spectacular project.
As the engineers changed the shape of the building to help counteract the wind, they discover a surprising side effect.
Because of the way we tuned the building, the way it moves, so that it doesn't amplify forces that we're seeing from the wind, we could go much higher than we started. It kept on getting taller and taller, even after the foundations were in and the bottom of the building had been started.
Changing the final height after construction has already begun is a bold move.
The tallest tower here in Dubai was only 33 floors. So imagine where we are now today. So for me, it was really like a dream.
But the extra height brings with it a new problem. As well as the tourists that visited, thousands of people live and work in the Burj. The building's capacity is 35,000 people, the equivalent of a small city.
One of the most important parts of a city is the transport network, and that's absolutely critical if you've got a vertical city like the Burj.
One of the major challenges in a tall building is how do you move people through it efficiently and quickly?
Stairs are impractical, although the Burj has plenty of them, nearly 3,000 in fact.
When it comes to vertical living, elevators really are the key.
But once again, the tower's extreme height means the solution isn't as simple as it seems.
In the past, the obvious solution many came to when thinking about tall buildings was to simply make sure every elevator went to every floor all throughout the building. And that at first seems to make sense. But if you've ever been in a hotel during checkout time on a Saturday morning and you were on the 7th floor of a 7-story building, you learn quickly that you will stop at every single floor. Your 30-second ride to the lobby is now a 3.5-minute ride. And that seems like an eternity. Now, magnify that by 160 stories.
To save everyone from spending half their day in the elevators, engineers turned to a solution inspired by city commuting.
You have express trains and you have local trains. And the express train takes you the 90 blocks you don't want to stop at. And you get off and take a local for the last 2 or 3 blocks that you really intend to get to. You can do the same thing with elevators.
Right in the heart of the building, nestled in the concrete core, are 57 elevators. 8 of these are express elevators that only stop at floors 43, 76, and 123, the so-called sky lobbies. From here, people can take one of the local elevators to all of the floors in between. To make the system even more efficient, 2 of the elevators are double-deckers. So as tourists make their way to the observation deck on level 148, others are riding to their offices in the car above.
We're in the heart of Burj Khalifa at this moment. Next to me, you see one of the biggest machines, or the biggest machines we have in the world, driving a double-deck elevator.
The elevators in the Burj are some of the fastest in the world, whisking people hundreds of feet up and down at 22 miles per hour.
The acceleration and deceleration of the elevators is controlled in detail. The idea of the experience is to let people not feel the movement.
This phenomenal speed also serves another purpose. The elevators form part of an evacuation plan that turns conventional wisdom on its head.
Everyone knows that in case of fire, you never take the elevator and you always take the stairs. But the Burj Khalifa is a bit different.
One particular elevator has an incredible travel of 138 floors. More than any other elevator in any other building in the world. This is the Burj's lifeboat. It is encased in thick, fire-resistant concrete and can take 26 people at a time safely down to the ground in less than a minute. Having a fail-safe emergency plan in place is more important here than anywhere.
I think the prospect of being stuck 160 floors up in the air, should anything happen, petrifies me.
Just next to the Burj Khalifa is the Address Tower, a 63-story hotel and residential skyscraper. New Year's Eve 2015. The address is engulfed in flames hundreds of feet tall after an electrical fire breaks out. In 2017, another Dubai tower, the unfortunately named Marina Torch, has to be evacuated after it too catches fire. For the second time in 2 years, hundreds of terrified residents are forced to flee for their lives.
They actually came around pounding on our door and telling us to get out, so that's when we knew to leave.
The Burj is twice as tall as the Torch and can hold thousands more people. Evacuating them all in the event of a fire would take far too long. So instead, engineers have designed the building itself to keep people safe for as long as possible.
They've created what we call refuge areas. So that means that people can go down a few levels of stairs, but then they're into these encased, enclosed rooms that, smoke can't infiltrate into them. They've got fresh air supplies, and they're fireproof.
These safe havens only work if people can reach them. The stairwells must be kept clear. Today, a routine test will see if the tower's specially designed smoke suppression system is working properly.
Ideally, this is a fire exit route, and it needs to be safe for whomever is using it.
In the event of a fire, fresh air is pumped into the stairwells at a higher than normal pressure. It creates an invisible barrier at the thresholds, preventing any smoke from getting past.
Although we have the machine very close to the door, the smoke won't enter.
Hopefully, none of the Burj Khalifa's safety equipment will ever need to be used. But here in the desert, the most dangerous heat doesn't necessarily come from fire. May 2007. Construction of the Burj Khalifa has been underway for 3 years. The tower is now nearly 1,500 feet tall. And a new stage of building begins, the installation of the glass curtain wall.
Just like people, on a tall building, you need a skin to protect it from the elements. Here you see the cladding of the building, the curtain wall.
The Burj's skin is made of glass and aluminum.
The individual glass frames sit within metal frames and are actually assembled off-site, and then are brought onto the construction site as prefabricated systems.
The panels must be hung one by one. Positioning all 2,600 of them takes 2.5 years. By September 2009, all the Burj Khalifa's cladding is firmly in place. There is more than 1 million square feet of glass, enough to cover a football field 20 times over. But all this glass creates a new problem for the Burj. Temperatures here in Dubai can hit more than a sweltering 120 degrees. Keeping cool takes serious effort, especially inside a giant glass building like the Burj Khalifa.
The surface temperature can get quite hot, almost as hot as boiling water.
If you think about an all-glass building in an incredibly hot climate where the sun is shining all day long, what you would have is the inside of your building would get incredibly hot, in fact, lethally hot, within a few hours.
But thanks to some clever technology within the glass itself, the mega tower doesn't act like a giant greenhouse.
Now, when you look at this building, it sparkles. All that sparkle is the solar energy that's not going into the building. It's being reflected off.
You have a pane of glass on the interior and a secondary pane of glass on the exterior coated with metal. The metal gives it reflective quality from the light.
These special coatings reflect more than 70% of the sun's heat. But the Burj needs more than just sunglasses to help it keep its cool. Stripping away the layers of the Burj Khalifa reveals miles of ducting, which carry cold air all around the tower. Wherever you are in the building, you are never more than a few feet away from an air vent. Moving this air around such a gargantuan skyscraper requires some serious grunt. So every few hundred feet, the tower has an enormous double-decker mechanical floor, which houses pumps so powerful, together they could inflate 13 hot air balloons in just a minute. But the Burj contains more than 65 million cubic feet of air. Cooling it all requires more machinery than even this giant building can accommodate.
The solution was to build a chiller plant, not just one, but two, off-site, to provide the cold water that cools the air.
This building might look like an Arabic fortress, but it is actually a high-tech cooling plant that supplies cold water for air conditioning to the Burj Khalifa. 250,000 gallons of water a day pass through these giant heat exchangers before being pumped to the Burj through underground pipes.
We receive the chill water temperature at as low as 3 degrees centigrade.
It's used to cool more water inside the skyscraper's own heat exchangers.
This is a whole room full of machines dedicated for air conditioning. This is the main one out of 14 we have across the building. If we lose them, we lose the cooling, period.
The air conditioning system isn't just for comfort. Without it, the building will quickly heat up to deadly temperatures.
When the temperature hits 50 degrees outside, the maximum you can sustain it is roughly 2 hours.
Keeping the tower habitable is essential, because it's not just a tourist attraction. For some lucky people, it's home.
It's more than just a statement. It's vertical living at its best. It's an engineering masterpiece.
The Burj Khalifa has 160 habitable stories, with more than 3 million square feet of mixed-use floor space.
There's hotels, there's offices, there's residential, there's shops, all kinds of things.
Our gorgeous, beautiful terrace. Now tell me, isn't this amazing? You feel like you're in heaven, really.
One of the most important parts of a city is services: water, gas, electricity, sewage. And if your city's vertical, then you've got to move all of that stuff vertically up and down to get them where they need to be.
Supplying a regular city with the amenities it needs is tricky enough. But here at the Burj, the problem is made much, much worse, thanks to the inescapable force of gravity.
160 floors is an awful lot of people, and all of those people require water, just living their lives and sleeping and washing and scrubbing their teeth.
The tower uses a colossal amount of water, 250,000 gallons a day.
If we were trying to move that quantity of water horizontally across the ground, then that wouldn't be that challenging.
But moving it upwards is. 1 gallon of water weighs around 8 pounds. So every day, the Burj Khalifa needs to lift 1,000 tons of it.
Trying to pressurize that water to go all the way up in one hit would be very, very difficult, very expensive, and just create too much of an energy demand.
Hidden inside the Burj's 14 mechanical floors are huge water storage tanks. Mains water is fed into the tanks at the bottom of the building before being pumped up the building in stages through 62 miles of pipes. At each stage, water is held in the tanks until needed, when it's gravity-fed to taps and cisterns on the floors below. But what goes up must come down.
In your home, wastewater, it just travels naturally by gravity. But in high buildings, you don't want it all cascading the full height of the building. Enormous pressure would be built up in the pipes.
If wastewater fell unchecked, it would be traveling at over 100 miles an hour by the time it reached the ground. So it is also carefully moved in stages.
That's managed by sewage holding tanks. So it drains into a tank a few floors below and then pumped out in a controlled way.
And the entire water system is soundproofed, so residents can't hear any machinations. But here, their comfort isn't the only consideration. In July 2007, the Burj Khalifa becomes the world's tallest building. But it keeps rising. 9 months later, it becomes the tallest man-made structure on Earth. But it still isn't done growing. Its crowning glory is to be a 700-foot metal spire.
The contractor couldn't get a crane that high to place the spire. So we decided to assemble the spire down inside the building. Then it was launched from the inside the building and then came out to the top.
With the spire in place, the Burj is now its full and final height. A mind-blowing 2,717 feet. That's half a mile tall. There is nothing on Earth anywhere close to this tall. It's nearly twice the height of the Empire State Building. And its nearest rival, China's Shanghai Tower, which is 600 feet shorter. But its extraordinary height has turned it into a target.
You might say that the Burj Khalifa is the lightning rod for Dubai. The spire gets hit quite often.
Dubai can be battered by terrible storms, and each one can potentially bring lightning strikes.
A thunderstorm cloud can contain 100 million volts, so if just one bolt of lightning hits a building, it could be immensely destructive.
With a building as unprecedentedly tall as the Burj, they didn't have the data even to work out how many or how large a strikes to expect.
For the Burj, lightning definitely strikes twice. In fact, it's been hit more than 18 times since it was built.
So the main challenge of any tall building is to figure out how to take that lightning, run it down the side of the building without letting it get inside the building, without letting it penetrate the building, until it can harmlessly reach the ground and cause no problems.
I'm not too much scary to go in there.
At the top of the spire is one of the most sophisticated lightning protection systems in the world. Today, one of the rope access technicians is going to check it for damage following a recent storm. It takes even an experienced climber nearly an hour to reach the top of the spire. Sensors on this lightning rod anticipate when a bolt is about to strike and send out a stream of charges to attract the lightning towards the rod, which works well if the lightning strikes the top.
Because the Burj Khalifa is so tall, lightning doesn't just strike at the top. It can strike anywhere across the building. It needs to be lightning-proof all around it.
Luckily, the tower has a hidden trick up its sleeve. The entire metal exoskeleton of the Burj Khalifa acts as a Faraday cage, drawing the lightning to the ground around the outside.
And this Faraday cage directs that electrical current around all the important stuff. The electronics, the people inside the skyscraper, without damaging anything inside.
The protective engineering has kept the Burj Khalifa safe for nearly a decade. And in this time, it has become a global icon.
The effect of this tower is immense. If you go out to the lagoon next to the building, any evening, every day of the year, there's thousands of people there to see the building, see the fountains, see the lighting show. It put Dubai on the world stage.
It started with a dream, and then a journey of seeing that dream every day getting built high and high and high.
From its unshakable foundations to the rock-solid concrete core, from its extraordinary protective skin to the ingenious solutions that allow it to function, this tower is an engineering marvel.
We're still the best, we're still the highest, we're still staying up there.
On my way here, walking over to the building this morning, I stopped to take a picture of this building that I know so well. I just have to. It's just quite remarkable.
The Burj Khalifa is one of the greatest superstructures ever built. Like no other, this enormous state-of-the-art building dominates the entire city that surrounds it.
The Singapore National Stadium is a truly epic structure.
It's simply, undeniably unique.
You have this beacon of light coming off the top of it.
The multi-award-winning sports arena is a dazzling symbol of Singapore's national pride. But more than that, its architecture on a scale never previously achieved.
It's the largest free-spanning dome in the world.
How on earth do you build a dome this big?
It's, a real marvel of structural engineering.
When it opened in June 2014, the spectacular ceremony marked the end of a torturous battle against the laws of nature. Physics, as well as the climate, and even the land the stadium is built on, presented a deluge of horrendous hurdles that came close to defeating designers.
Obviously, it's a major project with huge challenges along the way to making it and realizing it.
The only way to find out how architects and engineers won the battle to turn the stadium into a successful reality is to take it apart and reveal the innovations hidden within it. The futuristic Singapore National Stadium is the centerpiece of a giant $1.3 billion sports hub. Dreamed up at the start of the millennium, the intention was to give the city-state a glossy new forward-looking image, with a stadium that could host prestigious international events.
Back in 2000, year 2000, Singapore was really looking at transforming itself. It is a red dot, little red dot in the context of neighboring countries and this part of the world. We may be small, but the dreams and aspirations of Singapore is actually very bold, very big.
Today, the stadium stands as a testament to those grand aspirations.
The National Stadium is the largest free-spanning dome in the world, spanning over 1,000 feet. The range of engineering disciplines that we were controlling was beyond anything I've done before in my career.
Designing a venue that delivers a great experience to tens of thousands of people all at once is quite different to any other engineering challenge. And for architects, a stadium can be the most creative project of all.
This is incredibly hard to do. It requires a vast investment in technology to engineer that. And so you have to have the right kind of geological conditions and the right kind of infrastructure systems in place to support the building, both during its construction and during its lifetime.
All of these buildings are one-offs. You're not
doing it as number 7 in a series of 10. You know, these are each unique buildings with their own constraints and their own set of reasons for coming up with various aspects of the designs.
The problems to overcome can be anything from crowd transportation to the sourcing of building materials. For the Singapore National Stadium, there is one issue that will never go away.
We are located in a tropical zone where it not just rain, it pours, cats and dogs, right?
In the 1970s, the first national stadium was built on the same site. But it was open air and completely useless against the elements. Right from the start, the brief for the new stadium insisted on a weatherproof roof. The architects could only come up with one solution. It was radical and would be a huge and very public gamble because it had never been attempted on this scale until now.
There's a huge amount of pressure, and you're always feeling that if it didn't work this time, then you didn't have an alternative.
To build an actual structurally sound, solid roof over a stadium is a feat of engineering of some distinction.
For starters, the area of a stadium roof is vast. And that means weight, lots of it. Several stadium roofs have collapsed.
You have to think about the obstacles you face whenever you enclose a stadium of any kind, which is how do you hold the roof up? And in most conventional stadiums, that was done with columns.
Columns are very effective for supporting flat roofs. But any column system inside a stadium has a fundamental disadvantage.
In a large sporting arena, the starting point for the designer is the field of view of the spectator. They want to be able to see what's going on.
You don't want a column interfering with the view of the fans sitting behind it of the action on the pitch. So how do you deal with that?
For the new Singapore National Stadium, any design with columns is ruled out. But a roof is still a requirement, and it must be supported somehow. Architects delve into history for inspiration.
Going back to sort of Roman bridges and the like, the arch has always been a very natural form for resisting uniform gravity loads. That's why they work well for bridges and even naturally, you know, the natural arches that would form in rock.
If you think about the arch, you've got this curved structure, and when you put a uniform weight on top of that arch, the arch basically channels all of that load into the bottom of the arch, but it keeps the entire structure in compression. So what that means is it's being squashed together.
You take an arch and just keep on rotating it, rotating it, rotating it, you get a dome.
Not only is that efficient for resisting a uniform downward load, because it's a three-dimensional system, it actually has quite a lot of resistance to buckling out of shape.
The architects choose a dome for the roof, but they go a step further and plan the entire structure to be contained in the dome.
As is the case with anything, with any building, scale matters. So sometimes when you do something that we know well, but you just do it a lot larger, the impact really is tremendous.
But what about the weight problem that a roof of this scale inevitably poses? The stadium's first secret lies underneath its outer shell. There are no supporting walls. The whole building is basically a roof, a lightweight dome formed by a number of gigantic metal arches. 6 steel trusses span from side to side, and at 90 degrees to them, there are giant transverse trusses. Together, they hold up the whole roof.
Trusses with lattice structures are structural engineers' favorites because they've got triangles in them, and triangles are really, really stable shapes. They don't deform. So if you imagine that you had a rectangle shape, and if you put kind of funny forces onto it, it can deform into a diamond, but triangles just don't do that.
There are over 11,000 tons of steel in this monumental structure. But in 2008, when the design team were still drawing up plans, the global financial crash takes its toll, and steel prices rise all too aptly, right through the roof.
When we initially did the design of this, we had almost double the amount of steel that was in the roof. And then as steel prices escalated, then there was a real drive to say, okay, how can we drive efficiency into this?
To stop the project going way over budget, the team urgently needs a revised design.
Our design mantra was to reduce weight everywhere in the structure of that dome, so we got the best, most efficient shell structure. Everything had to be optimized to the minimum weight to make that a very efficient dome.
They create an innovative computer program that can work out the minimum amount of steel that would still meet the structural requirement.
We developed a very bespoke piece of software to achieve optimization of every element within that roof structure, whether that was the thickness of the steel or the diameter of the tube. It was all optimized to make it the lightest steel structure possible.
20, 30 years ago, you just couldn't do that. It would take you years to do the sort of design that we've done here in a matter of months.
The result is a world record-breaking dome that is so large the Sydney Opera House would fit inside it.
All of the sections are hollow, so they're all hollow tubular sections. You make them as thin and as light as you can. You're up here and you're looking at it at various angles, and everything just looks right and it looks in balance, and because everything is here for a reason.
Reducing the amount of steel cleverly saved the budget going bust before construction had even started.
If you took all of the steel in the roof and you melted it down and laid it down on the footprint of the building, you'd only have 15 millimeters of steel.
The structure that makes it up looks really light and elegant and slender. So I think it's, a real marvel of structural engineering.
One challenge down, but the roof design is just the start. Making it hold its own weight is one thing. Firmly attaching it to the ground is quite another. When the high-tech Singapore National Stadium was built, the construction team faced a serious problem. The local terrain was completely unsuitable for erecting a large, heavy building.
Because it's reclaimed land, directly underneath the grass and the topsoil here, we have a lot of what's called marine clay, and marine clay is about as useful as dark grey toothpaste to build a building on. It really is just muck. If you were coming down onto rock, the force from a dome could go directly into the rock. We don't have that advantage here.
The poor ground threatened the whole project, but there was a clever solution right in front of them.
We started with the demolition of the old stadium here in late 2010. The old stadium was crushed up.
All of the concrete was used as either a base or some parts of the ground forming for landscape.
And on top of that debris, a rock-solid base of concrete.
The Singapore Stadium is built off what is called a raft foundation. Now that is a large concrete slab over the ground.
Unfortunately, the raft foundation alone is not enough. The dome's weight pushes out as well as down. It would collapse into a giant pancake unless something holds it in. Once again, the engineers look to historic masters for inspiration.
In historic domes, like Florence Cathedral or St. Paul's, is a chain, a metal chain. So you put a metal chain around the edges, so where all the weight of the dome comes down and is trying to pull out, it's restrained.
Engineers stole that Renaissance concept and came up with what's known as a ring beam. Instead of using a chain above ground, they buried it in the foundations.
In the Singapore Stadium, the dome is restrained at the edge by steelwork. that it must be completely continuous, as if it were a chain, to stop the dome pushing out. It relies upon being one structure with complete undamaged integrity.
So what I'm standing on the edge of at the moment is the ring beam, and it contains 14 ducts of very high-strength steel cables. And those cables, the amount of force that we put in those, we pre-stress them, is around 4,000 tons. So it's a huge amount of force. The ring beam is like a large, very strong elastic band that's pulling it back in so that all those legs don't spread.
Most critical is where the huge trusses meet the ring beam. A single error here, and the trusses would explode out.
So these are some of the most complex and nerve-wracking parts of the project to construct, and we call them the thrust blocks. So the entire roof, which is 9,000 tons of steel and around 15,000 tons total weight, comes down on only 20 of these supports. So you can imagine how hard they're working.
The weight of the whole structure is directed down onto these huge thrust blocks. The only way to understand how they're locked onto the ring beam is to look inside one of them. Hidden within the giant concrete block is the secret. 175 metal rods called shear keys penetrate right into the heart of the ring beam. Their length and diameter perfectly calculated to be just enough to completely secure the truss.
Bringing this down just to get 175 shear keys to sit inside that reinforced mat was one of the most challenging elements of the whole job.
The next aspect of the project is where the real headaches start. The pitch is made of live grass, which leads to another complex engineering problem. The enormous roof has to open and close.
The moving roof did pose challenges for us. You know, quite commonly they're done on a flatter roof profile, and they're very linear in their opening and closing arrangement. Doing it on a sphere created some real challenges for us.
The movable sections each cover 100,000 square feet. And because they're curved, getting them to move at all is a mechanic's nightmare.
The retractable roof is around 1,000 ton per leaf. There's 2 leaves that open and close, so the roof had to be very strong and very stable.
The design was for the movable leaves to run on rails. But there was a dilemma. Any expansion or contraction of the metal components could make the panels jam. So they couldn't be too rigid.
We worked out very early that we should have a very stiff fixed roof, but then kind of a floppy retractable roof that could kind of bend and move a little bit.
The solution that engineers ended up using was an incredibly efficient winch system, with winches mounted on that retractable roof to reduce the amount of cable that was required.
When you are wheeling in, it pulls the roof upwards to close. When we are lowering the roof, majority of the lowering, the work is done by sheer gravity.
The roof panels are mounted on rails attached to the arched trusses. Powerful winches on the base of each panel heave them up to close the roof, and the cables take the strain when it opens. But here's where it's really smart. Sensors monitor exactly where the panels are, preventing them from ever skewing more than 1.5 inches. And to reduce friction, the number of wheels in the system is kept to a minimum.
If we reduce the number of points that it actually hangs from, or the driving points, then that also reduced the possibility of the whole thing jamming.
This silver-looking strip is like a barcode, and the position sensor actually reads off this silver strip to inform back to the event control room where the control system is at on the position of the roof at any one point of time. So this is tracked very closely. And one fun fact is that it's so sensitive that even a drop of water would actually cause the entire system to stop.
The retractable roof is a key feature of the stadium. Incredibly, it can open or close in just 20 minutes. Thanks largely to lightweight inflatable pillows of plastic called ETFE, which make up its skin.
Basically, all aspects of the roof movement is actually controlled here from the event control room. We've already done our last checks. Mission control is good to go, and we hit the button.
Operating such a huge structure, it's better to have as little heavy elements as possible as we can. One primary reason why it needs to be inflated is to allow water to run off, so that it's not a flat surface. If it's flat, water can collect, or if it's sagging, water can collect.
Today, the maintenance team are out, using a drone.
Actually flying above and outside of the stadium because we actually get to go to places where even the rope access technicians would have great difficulty getting to. So over there, we are actually able to scan the entire outer shell, outer dome of the stadium itself.
If you're in the tropics or you're equatorial like we are here in Singapore, and you're coastal, then you have salt in the air, you have a hot, humid environment, things rust very, very quickly.
So with the drone, we're actually able to go up there, start to inspect for things, see whether there, let's say for example, are there any abnormal rust streaks coming down from the roof? Are there any panels that look misaligned? Is there anything that really looks out of the norm? On occasion, when the pitch is in, we actually use it to monitor the quality of the pitch and to actually see how well the grass is growing on a frequent basis.
Keeping a vigilant eye on the state of the turf is vital for any venue that holds world-class soccer, rugby, or cricket events. But for the Singapore Stadium, it's now especially important, because soon after the pitch was planted, there was a disaster.
Unfortunately, there just wasn't enough light getting into the stadium, and the grass, it died.
The Singapore National Stadium is one of the most high-tech sporting arenas in the world. But when it opened, it had serious teething problems with one vital component: the turf.
In any sports stadium, the pitch will be the crown jewel, because this is where all the football action, rugby action, all those events or activities happen here, and you have a full house of 50,000 people watching. So I would say the pitch would be most important.
One of the huge challenges building a stadium like this is that you've got a living thing at its centre, this huge lawn that's got to be kept in absolutely tip-top condition for international sporting events.
Because we are located in a tropical zone, because we have a retractable roof, it is not so simple to just grow grass in this climate.
So the 5 key elements of growing grass: you need light, water, temperature, air, and of course nutrients. So to keep this grass healthy, these 5 elements are important. In a dome where we have shade and all that, first of all, the light is compromised.
When the stadium opened, disaster struck. At the centre, the crowning glory of this stadium is its beautiful, flat, international quality grass pitch. But unfortunately, there just wasn't enough light getting into the stadium, and the grass, it died.
More than an embarrassment, the withered grass threatens the fundamental viability of the stadium. Detractors call it a white elephant, a colossal waste of money. Footballers like Carlos Tevez are prevented from playing on the substandard turf.
When it got to the point that managers weren't allowing their star players onto the pitch for fear that the terrible sandy condition of it would cause them injuries, something had to be done.
Initial days, we used the stadium growth lights to enhance the exposure of light.
This problem with the grass was so fundamental that they tried everything to solve it. And they spent a phenomenal amount of money trying to just blast this grass with artificial light to help it grow.
But the light isn't the problem. The grass still stubbornly refuses to grow properly. Desperate for a solution, they take a major gamble and commission a brand new type of turf.
We are now currently at the nursery where I grow all my grass, my peaches. And this is where I do all the work, the start of the journey, before all the grass rolls, get all rolled up and go into the National Stadium for events.
At an off-site location away from the stadium, Jonathan and his team of horticulturalists experiment with different types of grass.
To some point, my family actually finds it quite queer and sometimes funny what I do. I get out very early in the morning and I come back when the sun is setting, and they do wonder what I do until I take them to the park and I explain to them the different grass type and how is it maintained, and they go, wow. We are doing a traction test here, and this is a portable traction tool. And as it rotates, we have a reading on the wrench here, and the time when we stop is when we hear the grass almost tearing, and we look at the reading from here. So a good traction will be about 40. So this is what we're trying to achieve, get it ready for the National Stadium.
Eventually, they choose a brand new hybrid turf that is part real grass and part synthetic fiber.
This is the section of the turf rolls of the hybrid system. It's reinforced turf. As you can see, there's some fibers that's intertwined with the turf grass. Of course, the grass matter a lot as well. It's just a combination of both. That's why it's a hybrid.
The big advantage of the nursery is that spare pitches can be grown here and transported to the stadium whenever they're needed. The hybrid turf has 7% synthetic fibers mixed in with live grass to give the cutting-edge playing surface consistence. A layer of high-grade sand aids traction, but it's a special woven backing that holds both roots and fibers together. A network of subsoil pipes supplies the pitch with water.
The irrigation system is fully automated. I have a computer system in the office where I can do my work and control it, or I can have a remote to control it, and as well as an app on my mobile phone that I can control it while I'm having breakfast. Yeah.
In the past 1 year, it's been very positive. We get definitely a sense of satisfaction of saying, okay, this strategy is working, it's coming along. But then again, there's never complacency because we are dealing with a natural product here.
The removable pitch is known as a lay-and-play surface. And for the Singapore Stadium, it offers up an added bonus.
We are pretty much a multi-events calendar where we got sporting, we got community events. So because of this, the lay-and-play solution was approached, and it works out very well for us.
They can change the pitch in just 48 hours. But whatever the event, there's one issue that always needs addressing: how to prevent spectators sweltering in Singapore's super hot temperatures. Singapore lies just 1 degree north of the equator, its tropical climate unforgiving. Humidity is consistently over 70%, and the temperature often soars well over 80 degrees Fahrenheit. To avoid the spectator experience being compromised by the extreme heat, the National Stadium's engineers must provide cooling on an enormous scale.
Imagine the biggest room in your house. We're talking about something thousands of times larger. You know how hard it is to heat and cool that room. Imagine trying to do it at a stadium of this scale.
Quite clearly, you can't condition the air from the top and blow it down, because it will just heat up again. One of the essentials about any form of heating or chilling, you don't want to heat or chill a space, you want to heat or chill people.
Rather than air conditioning the whole enormous volume of the stadium, what the engineers came up with was a per-seat addressable system.
Remarkably, cooled air is blown individually to every member of the crowd from below.
The air is being pushed out through below the seats, and you're getting the effect of that as a blanket of cold air local to the seating tier, not trying to cool the whole volume of the stadium.
Pull out the seating, and there is an intricate labyrinth of tunnels. Ducts that send cooled air to outlets beneath every single seat.
So using the concept that hot air rises and cold air sinks, we are able to keep the cool air in the stadium by pushing through the seats outlets and downwards to all the audience. Okay, if you put your hand here, you can actually feel the cool air coming out from the seats.
It's a brilliant idea, but the ducted air still needs to be cooled somewhere.
We have 116 air handling units located at the back of house that provide cool air to all individual seats in the stadium.
Warm air from the atmosphere draws into these giant heat exchangers, where it meets cold water.
Behind me are the chiller plant room producing chill water. And once this chill water leaves the plant room, it travels through the pipes to the individual AHUs, air handling units, so-called.
The challenge here is how to produce very large quantities of cold water on demand.
So one of the solutions they've come up with is to use loads and loads of balls of glycol, so basically antifreeze, which you cool down to a very low temperature before a game, and that means that you can use them to store up all that cold in readiness for the big event.
Glycol works like the ice packs we put in the freezer. It retains cold.
Night before a big match, they'll cool down the glycol, which in turn can cool down the water, and then this water will cool down the warm and humid air, which is then circulated out into the stadium.
Once the cooling is achieved, the water simply recirculates through the system. When the Singapore National Stadium was conceived, one of the most demanding directives was that it should be a multiple function area. Like no other stadium on Earth, it must host soccer, rugby, cricket, and athletics, as well as rock concerts. Each kind of event needs a different sized area, but for all of them, spectators need to be as close to the action as possible.
The only way to make sure people are right at the forefront of the action in loads of events with very different configurations is to allow the seating stands themselves to move. The first thing that happens is that middle tier retracts downwards, and then the front tier of seats can move back, covering those up and making a bigger space in the middle of the stadium.
There's 30,000 seats that move. In athletics mode, they drop down to the ground and they're tucked under the retracted seats. And there's about 5,000 seats that appear in football mode.
The tiers weigh up to 1,500 tons each. So this is an incredible feat of engineering. Hidden underneath the seating bowl is a state-of-the-art lift system.
That's called a Serapid machine. It's a chain-driven machine that crawls around in a trench.
With the help of this machine beneath the tiers, the stadium's capacity transforms 50,000 to 55,000. And for both configurations, designers have maximized the spectator experience by scientifically designing the acoustics. In public arenas, spectators demand excitement. They want a high-volume assault on their senses.
It's always about creating the unforgettable experience for spectators. In the Singapore National Stadium, we've achieved something really special in terms of atmosphere.
An important aspect of that experience comes from the stadium's acoustics.
You want it to be noisy. If you're cheering on the Reds, you want to hear everybody else cheer on the Reds, and the louder the noise, the better.
Acoustics are incredibly challenging because you're dealing with different types of events. So you're dealing with concerts, you're dealing with soccer events, you're dealing with different capacities within the venue, so you have to design for absorption on people being in the bowl or how the sound will be reinforced within that atmosphere.
Here in Singapore, sound engineers applied rigorous science to the choice of materials for the roof. Anything that would absorb sound, like soft curtaining, was rejected.
You want to hear that crowd magnified, amplified. And so in the Singapore Stadium, they've got loads and loads of highly sound reflective surfaces that bounce that sound back at all angles to try and make everything sound as loud and intense and vibrant as possible.
It's very important to have lower part of the roof to be reflective, which can reinforce this excitement generated from the crowds.
Today, Jingfeng is running a test to determine if those reflective metal and plastic surfaces are still performing as intended throughout the stadium.
We're going to play a special test sound to check the frequency distribution at each receiver location, as well as how evenly the sound level is across the stadium. The special sound we're going to play is pink noise, which is a flat sound across the overall spectrum.
Pink noise is sound that's evenly spread between low and high frequencies. If the monitor shows a flat response, it means the space is reflecting all frequencies equally. Any drop-off shows that frequency is being absorbed. The results are all pretty flat. Good news. When a stadium is at full capacity, it is particularly vulnerable. And that means crowd management has to be at the very center of every design decision.
And when the game's done, everyone's out. And so it's 55,000 people on leave now. Modeling that so that you understand how people can do that comfortably and leave and get to the various transport facilities within a reasonable time frame and comfortable and safely is absolutely critical.
The price paid when things go wrong is the heaviest imaginable.
In a stadium, when it's full, you've got tens of thousands of people all in there at the same time. And we know that we've had some really devastating disasters in the past, whether it's Hillsborough or Hazel.
At both tragedies, critical errors compounded and people were crushed to death. And if fire takes hold at a stadium with poor exit planning, the results can be equally shocking.
And we saw that to our cost at the Bradford Stadium, where there was a terrible disaster about not being able to get people out.
Fires in these sorts of facilities are very, very rare, but the history in the UK has shown that they can occur, and understanding how people will react and making sure that they can react and they can leave safely in a very short period of time is critical as well.
We've designed the building so that the typical scenario is evacuation in terms of a fire or something which requires an immediate local response. And for that, we have an 8-minute time frame in which we're allowed to take people from their seat to a point outside of the stadium.
Planning how 55,000 people can quickly evacuate the stadium is a task where the architects couldn't afford to make a single mistake. A life-threatening emergency at a crowded stadium is one of the greatest fears for any architect.
So it's absolutely imperative that the design of the structure and everything that goes around it is really spot on to make sure that we don't have any devastating consequences from it.
Singapore Stadium's engineers used computers to analyze crowd behavior and help them plan entrances and exits.
These things are amazing to watch because you watch where people crowd and where they congregate and where you're getting too many people, where are the pressure points. And it's really important to find where that's going to occur and then change the design before you've built it.
Part of the design of stadiums is around ensuring that every exit, as you sequentially go to the outside of the building, is getting wider, so you're sequentially able to flow unimpeded at a faster rate out of the building. And a lot of that required us to make changes to the design because some of the widths, even 10-metre widths, were required to increase to 12-metre widths to allow for counterflow of people under the cover of that canopy.
The status of any stadium is defined by the prestige of the events it holds. One of the most impressive staged at the Singapore National Stadium was the 2015 Southeast Asian Games.
That was a very successful event, and it really showcased how the stadium can be best used for those sorts of events. That was something where the people of Singapore came and really, I think, felt a wonderful atmosphere in here, and I mean, it's their city on display to the world.
But in this day and age, even a world-class event is not enough to draw attention.
Increasingly, stadiums are urban projects that help give identity to cities, and so therefore you want them to be prominent in the skyline and prominent in the cityscape.
So for me, the most impressive thing about the Singapore National Stadium is those plastic cushions at the top that light up and just give the building a huge amount of personality. Right at the crown, at the top of this beautiful dome, is this absolutely startling feature where they use lights to project images and videos, which you can see not only from the inside of the stadium, but also outside from the city itself.
The fact that we have a live roof is very unusual, but it adds to the enhancement of the patrons' experience. So, and this is what we aim. We want to give the patrons, as they're coming in, they can see a lit roof, and once they come into the stadium, it's even a better experience for them.
When there's a goal and it says score and goal and it flashes from one side to the other and there's all this rock music and everything going on, it just really pumps up the crowd, and that's important for the stadium to be successful, but also how it's conveyed on TV for viewers at home.
So in order to create this really impressive display, they've used tens of thousands of LEDs on the retractable portion of the roof.
The vast screen is one of the largest in the world. And because it's made of LEDs, it draws comparatively little power. It's the final piece in this high-tech puzzle and cements the stadium's high profile. Not only is it the largest free-spanning dome in the world, it's prevailed against all its detractors and become a triumphant sport, entertainment, and economic success story.
Stadiums are so expensive, in part because they're among the most profitable buildings you can build. Essentially, a stadium is a machine for making money, which is what we used to call skyscrapers. But I really think stadiums have supplanted skyscrapers as the ultimate 21st century machine for making money.
Against the odds, the Singapore National Stadium has overcome the problems of building on soft reclaimed land. It has a roof of unprecedented scale, and extraordinary engineering enables its seating tiers to be transformed on demand.
I think the emotional part is that it's come true. It's a dream come true. It is one that it will transform our lives.
Just an amazing venue which we, as a team, just incredibly proud to see open. And it is about an integrated approach to architecture, design, with engineering to achieve what we've achieved.
Beneath these roofs, there are more square feet of car production than at any other factory on Earth.
Making a car, it's the great master arts of the 20th century.
The Wolfsburg plant in Germany has over 12 miles of automated assembly lines manned by around 6,000 high-tech robots.
It takes really ingenious engineering to make everything happen smoothly. Every 16 seconds, a finished car leaves the production line.
Even that is not enough. The plant now aims to build 1 million cars per year. From the outside, it's impossible to tell what engineering innovations could make this incredible target a reality. For decades, the red brick production halls of Germany's Wolfsburg car plant have set a benchmark for factory design.
The sheer size of this factory is astounding. The area is nearly 3 times the size of Monaco.
These are more than 100 workshops on this site. It is like a self-contained town.
Inside this factory, there is everything needed to turn raw materials into finished cars at extraordinary speed.
It would not be possible without highly efficient, highly state-of-the-art machinery. This is a result of 80 years of relentless development and advancement in technology.
The plant's current success negates a dark past. It was founded just before the Second World War, specifically to make the cheapest cars possible.
Right behind me, this is the original part of the factory as it all began in 1938.
The Nazi Party had swept into power. One of Adolf Hitler's ambitions is to give his followers mobility by creating a people's car, or Volkswagen. So he enlists car designer and future Nazi Ferdinand Porsche.
Ferdinand Porsche worked very closely with Adolf Hitler in the creation of the original Volkswagen. Hitler set for Porsche very serious demands, and most challenging of all was his requirement of a selling price of only 1,000 marks. Now, 1,000 marks in those days might have bought you a used motorbike.
At the time, German factories like Opel's Rüsselsheim plant couldn't build cars cheaply enough. There was only one solution, a brand new plant built for a revolutionary type of manufacturing.
If you want to make a large number of cars quickly and cheaply, then mass production is really the only game in town.
Real mass production was not known in Germany. Porsche realized that if he were going to meet these goals, he would need to know more about how American cars were manufactured.
Porsche heads to America to meet Henry Ford, the mass production expert. His Rouge River plant is legendary for speed and efficiency. And crucially, it has its own rail network.
Porsche took away from America the most advanced production facilities and concepts that existed at the time. And they incorporated them in the design of the new factory.
But the Nazis had a problem. Where to build their new factory? It had to be centrally located and have good transport links. They settled on Lower Saxony, an area well served by railways and close to an iron mine.
Well, the site was situated here because it was in the middle of Germany in 1938, and everything that was needed to manufacture cars was available out of a surrounding distance of around 30 miles.
Construction begins on one of the Third Reich's most ambitious projects. Taking their cue from Ford's factories, they build an imposing function-driven complex with regular bastion-like external stairwells, skylights throughout, and even a dedicated power station.
The production volumes that they aimed to reach, up to 800,000 cars a year, were far in excess of anything in Europe, and in fact exceeded most of the car production by companies in America.
The Nazis pour over $500 million in today's money into the factory and start building an entirely planned new town for thousands of workers. In just over a year, the first 4 halls are ready to start making Hitler's Volkswagen, the car that would go on to become known as the Beetle.
They invested in the very, very best equipment. They had an extremely advanced press shop. They had one big press that could stamp out the whole roof of the Beetle.
But Hitler then starts the Second World War, and the Wolfsburg factory is repurposed to make military vehicles and munitions. The Nazis staff it with forced workers. Many come from concentration camps, and they are brutally treated by the factory's SS guards. In 1944, the factory is almost destroyed.
During the war, the factory was bombed, and a fully loaded Lancaster bomber had piled into the biggest hall and gone through the roof and caused tremendous damage.
Instead of that being the end of the factory, it's rescued after the war by the British. In 1945, Major Ivan Hurst oversees repairs and arranges the order of 20,000 of the strange cars the plant had been designed to make. The Beetle press equipment had been spared, so the factory quickly starts production.
It hadn't 4 doors. It had the engine in the wrong place. It had not enough trunk space. It had not enough heating. But fortunately, the customers from all over the world decided differently. We started producing first in December 1945, and 10 years later, we produced the first million Beetles, which was an unheard number in Europe.
Despite its failings and its association with a Nazi dictator, the Beetle becomes a worldwide sensation. By 1972, it is the biggest-selling car of all time. And as its popularity grew, so too did the Wolfsburg factory. Today, it has more than tripled in size. It spreads across 70 million square feet, the largest area of any single car plant in the world. The brick production halls still form the heart of the operation. But the Beetle presses have been replaced with 4 gigantic press shops, making almost 500,000 body parts per day. And the assembly lines are now staffed by about 6,000 high-tech robots. Every day, they're capable of assembling up to 3,500 cars. The original power plant has been expanded, and linking this vast site together is an extensive private rail network.
This is Europe's largest private train station, and there's more than 40 miles of rail tracks on the factory premises.
Every day, more than 1,600 tons of steel is brought into the plant.
Altogether, we have 11 wagons per day coming in with raw material.
It is an incredibly challenging task to deliver all the freight into this factory.
Directing each train to the right part of the plant would be impossible without a sophisticated control system. managed from this tower.
We have 3 colors of lines. On the yellow line, we have 3 tracks. On the red lines, we already have some rail wagons standing. And on the blue lines, like here, are actually trains driving.
The operator has control of 150 shunting switches, which allow trains to change lines and head directly for their allotted destination building.
For efficiency, the trains are transporting the materials right inside the workshops.
This train is delivering 24-ton rolls of raw steel. Once inside the depot, specially made cranes unload the rolls directly from the train carriage and place them on giant cutters.
So the first step in manufacturing is turning that raw material into components. We would take the uncut steel and form the shapes of the door, of the hood, the trunk, the wing. So the first challenge is to keep up with the pace of production and assembly. You need machines that are fast enough. The equipment used to build the original Beetle could never cut it.
The original Beetle presses were enormous machines that stamped the body panels into shape.
It used to be pretty exciting to see operators putting sheets into these presses and then standing there as this immense press comes down.
But these presses had a major drawback. They had to be loaded by hand.
We're just losing time at every step, while those human operators try to meticulously line up that steel to make the perfect final component.
Today, the factory must produce 10 times the number of cars it used to when it was making the Beetle.
Manual feeding could not be plausible today in a press shop.
There's no way that hand-fed presses can make parts fast enough. Germany's Wolfsburg car plant is more than 16 million square feet larger than its nearest rival, South Korea's Ulsan Auto Factory. And demand for body parts is relentless. Housed in the rear hall of the original Wolfsburg factory, enormous pressing machines need to spit out more than 5 body panels per second.
The press shop at the factory is serving not just this factory, but the group across the world. Almost 500,000 body parts get manufactured there a day.
This phenomenal output is thanks to a revolutionary panel pressing system. 6 of the heavyweight industrial beasts are linked together. Mechanical arms with suckers maneuver the steel from press to press, with more precision and speed than people ever could.
They're linked together almost as in one machine, and then the steel can move through each press automatically to form the correct shape and part.
These presses are enormous, and in order to exert enough pressure to bend the steel, they need to press down with a force of about 8,000 tons. The only way to generate a force that big is to use hydraulic pistons to squeeze those presses together.
Each press slams the steel plate further into shape, and the line delivers a constant flow of identical panels. But unfortunately, linking the presses only solves one problem.
Obviously, the factory needs to make all the different components for a car, from the bonnet to the doors to the roof. And you can't have a separate press street for every single component. It's just not feasible.
Each press shop must be versatile enough to make different components.
Inside each press is a die. They're actually what forms the shape, the cookie cutter of the component.
To make different parts, new dies must be swapped into the presses. But it's a massive operation.
Traditionally in the industry, it took about 2 to 3 hours to change the dies because it's quite a difficult job. The machine is sitting idle during that whole period. It's not doing productive work.
Leaving presses inactive for long would slash production. Engineers had to come up with a solution.
New processes have been developed to reduce this changing period from a matter of hours to a matter of minutes. There are doors on either side of the press street. The replacement die is craned in onto rails. The door opens and the old die goes out and the replacement die simply rolls in. It is no longer something that stops or slows the production process.
The presses can now run almost 24/7, but this puts tremendous strain on the machines.
The dies are not necessarily delicate. However, it is machinery, moving and grinding almost non-stop. So equipment can wear, problems can arise.
A single press malfunctioning could be catastrophic.
If the presses would break down, we wouldn't have the body parts to make the body shell, and everything would stop.
But maintaining them is easier said than done.
These panel pressing lines are enormous, fast-moving, heavy, noisy machines. And that means it's incredibly difficult to find faults before they arise. They don't want to stop the machine and go in and check it. So there needs to be a way to identify those faults before they become serious in this incredibly challenging environment.
One innovative way that faults can be identified is by listening to the machines.
Nope, perfect. This is the acoustic camera from the press shop Wolfsburg. We have one camera and 48 microphones.
The acoustic camera is pointed at one of the press shops, where it can listen to a machine as it runs.
What just sounds like a huge machine clanking to you and me actually has a unique and precise acoustic fingerprint, which this camera can listen out for.
It's like the doctor who checked the heartbeats from the patients.
The camera produces a waveform, a visual representation of the sound the machine is making.
Any deviation from that acoustic fingerprint recorded while the machine was working normally allows them to narrow down exactly what might be going wrong and diagnose problems before they become serious.
Mit der Kamera kann ich Anormalitäten sichtbar machen. Das heißt, wenn ein Lager ein nicht normales Laufgeräusch macht, was für den Menschen gar nicht zu hören ist, für die Kamera ist das kein Problem.
Today, the waveforms match. There are no faults. The factory's next challenge is to put all the components together to make cars as fast as possible. Body panels and other parts travel about 3,000 feet to the halls near the power station, where a daily engineering ballet takes place on the assembly lines.
So Wolfsburg's goal is to increase production to nearly 1 million cars a year. So to get anywhere near that number, it means employing robots, and in their thousands.
Each car comprises around 10,000 components, so putting them together is a Herculean task, even for a forest of high-tech robots.
This can be like watching a great performance. The sounds moving in sync, in harmony, and the dancing across the rhythms. It's almost like a hypnotic state, although it's super highly programmed and planned right down to the last detail.
Each individual part must be fixed not just in the right place, but also in the right order. And this largely automated assembly line is one of the fastest there is, the result of an extraordinary evolution.
Assembly lines are absolutely central to the concept of mass production. They allow creating a product to be split up into a series of discrete steps, and then they can work one after the other, continuously assembling products as rapidly, efficiently, and cheaply as possible.
The first assembly lines revolutionized car production with a simple idea. Instead of making workers move from one stationary car to another, the car moves on a conveyor to stationary groups of workers.
This did create a big increase in efficiency, but really it's nothing compared to what we would later see with the introduction of robots and automation.
But programming robots to be faster than people is a difficult, highly complex task.
So the human has hundreds of thousands of years of trained experiences, visually, sensory, and motor skills. And to put this into a robot is very challenging.
Germany's gigantic Wolfsburg car factory relies on assembly lines staffed by around 6,000 robots. The first was introduced here in 1973. It could only perform simple welds. Just a few years later, robots are omnipresent on assembly lines. But the brute force some are capable of is a serious hazard.
They are potentially dangerous and can cause injuries to humans that are moving in the same workspace. You can see that 200 to 400 pounds of payload can actually harm seriously the human.
There have been fatalities. On January 25, 1979, Robert Williams, an engineer at Ford's plant in Flat Rock, was struck on the head and became the first person in the world to be killed by a robot.
So the robot that would have killed Robert Williams at the Ford factory back in the 70s would have been a pretty simple robot by today's standards. So one of the things that really changed the intelligence of the robot itself is the microchip.
At a cost of at least $100,000 each, these super smart robots are some of the most dexterous. Inside each of their joints is a step motor. This rotates in small increments, and the arm can hold its position without the needs for brakes or a clutch. The software that runs the robot's onboard computers took more than a year to write, but it enables them to move in 6 axes, only one less than a human arm. They can spot weld, clip, or apply glue with exceptional accuracy.
They're very good at repetitive tasks. They don't get tired or bored like humans would.
Robots execute these tasks 24/7 over an entire week, as often as needed, at a very high quality, at a very high accuracy.
These are, in many cases, very large pieces of machinery, and there have been some examples, unfortunately, of tragedies even in recent years. In 2015, in Kassel, in a factory in Baunatal, there was a worker who was crushed under a metal plate, for example. These accidents, they are accidents, they still happen, and robots need to be treated with respect.
Around 65% of Wolfsburg's vast floor space is dedicated to these assembly lines, where the aim is always to get the robots to work faster. But the relentless high output can become the victim of its own success. It creates a fundamental dilemma: how to keep the robots supplied with components.
It's an enormous challenge to coordinate that all components and all parts are just in time at the right place of work at each assembly line.
Traditionally, parts were stored next to the assembly line.
If you do that, what you end up with is a warehouse full of parts waiting to be put into cars. And that's what the Japanese call muda, or waste. The first time the Japanese went to Porsche to look at their operations, they looked around and they said, "Where is the factory? This is the warehouse." Because along the assembly line there were big boxes of parts waiting to be put into cars.
At Toyota's Karamo factory in Japan, Kichiro Toyota was the first to develop a radical new system that does away with the need to store any parts at all. It's known as just-in-time delivery.
The concept today is to make the part, install it, and do it quickly and not waiting around.
It means that each robot receives parts just when it needs to install them and not before.
The fact that you don't need to store loads and loads of components just in case means that you can save a lot of money and space on warehouses.
It's hyper-efficient, but it's also high risk.
You need to make sure that every single stage of the process is perfectly optimized, as the name suggests, just in time, because any slight delay can radically delay the whole of the production line.
It only takes one bolt to be delivered late, and the entire system will grind to an expensive halt. Orchestrating it is a colossal task that takes place at the factory's control room.
We're standing here in the middle of the brain of the Wolfsburg factory.
Computers break the assembly line down into distinct beats that are completed at different stations, roughly 20 feet apart. After the chassis is completed, the doors, roof, and hood are attached.
So the assembly line has an average beat of 60 seconds. And this means that in every beat, another part is installed. The parts have to be in position at exactly the right moment to make sure they're installed in time. We achieve this by delivering the parts in an exact sequence.
The drivers follow a strict timetable. But there are over 10 miles of potential delivery points in the factory.
The robot waits for no man, or machine for that matter.
The factory roof is fitted with a monorail system capable of delivering 100 parts per hour. Any mistakes will cause problems for robots further down the line. But that's nothing compared with the danger inside the sealed paint shop. Inside Germany's colossal Wolfsburg factory, cars travel more than a mile along assembly lines before the body shells are complete and they reach a stage known as body in white. The cars then head north, past the power station, to a hall that's too dangerous for workers to enter.
In a modern factory like Wolfsburg, there are indeed several stages of production in which there are almost no people at all.
Painting releases noxious fumes, but robots are immune.
Painting the body of a car involves usually introducing the particular car into a closed room.
At this paint shop, specialized automatons first dunk the cars into an electrostatically charged undercoat bath.
There are no health issues because we don't have any humans inside this workspace, so the human is actually protected from all these fumes.
Automated gas burners then warm panels to aid the adhesion of top coats.
With Wolfsburg striving to increase production to 1 million cars per year, it does mean that every production stage needs to be highly optimized and use as much efficiency and automation as possible. However, that doesn't actually mean that every stage and process is currently automated, nor will it necessarily be automated.
In addition to all the robotics, the plant has a workforce of more than 60,000 people. The most complex process is building the powertrain. It takes a battalion of highly skilled workers to turn the engine, clutch, gearbox, and drive shaft into a single unit.
The powertrain in a modern car is incredibly complicated because it's made of loads of different components, everything responsible for getting that power from your fuel and converting it into motion.
It has its own dedicated assembly line, which must be perfectly coordinated with the car body it will eventually be installed in. This is a high-risk process, the ultimate just-in-time delivery.
There's no room for error. Every car has its own unique powertrain, and it has to meet the line at exactly the right point for the assembly process.
To make it even more of a challenge, the body and the powertrain are made on different floors.
So the powertrain is made right below this level. There's another level of the production where the engine, the gearbox, the exhaust, the axles, brake lines, where everything is put together to one unit.
timing is everything. Each of these skilled technicians has to know exactly how long they can spend on each task.
Before the chassis and the powertrain come together, the chassis is basically just a rather elaborate lump of metal. When those two things do finally join is known as the wedding.
At the exact prescribed time, robotic arms lift the powertrain through a hole in the floor.
And this powertrain unit is then arriving here just in sequence. That means at the moment the body shell, which is supposed to get that powertrain, arrives, and then the powertrain is lifted up by an elevator from the ground floor to be fitted perfectly into the body shell.
The wedding sounds incredibly romantic, and it's the first time that this thing becomes a car.
The powertrain is like the groom, and in this case, just happened to be a white bride.
Achieving a successful wedding would alone be a marvel of engineering and logistics, if Wolfsburg only made one model of car. But they don't.
The consumer wants to not have the same car as the neighbor, for instance, but they want to drive a very individualized car. So they cannot just produce one car model across the entire line, but there has to be a certain variability.
This factory is making so many different models and specifications of car that it's incredibly difficult to make sure that the right chassis and the right powertrain always meet.
One of the reasons for this factory's exceptionally high output is that different models of car can be built on the same assembly line. But how do the robots know which powertrain, for instance, to install onto which body shell?
The robots on the line are actually capable of making multiple different types of cars. And in Wolfsburg, we see 6, 7 different models, and several of those models come down the exact same assembly line. And the way these robots are so adaptable and can be programmed in so many different functions is really quite amazing.
Every chassis might look similar, but as each one enters the assembly line, a scanner reads a tiny tag attached to its rear, called a radio frequency identification tag, or RFID. This is the secret. The tag holds all the information needed to build the car. The model, the specific set of components, even the color.
They are very similar in a way to the barcodes that everyone knows from the supermarkets. However, these chips are more intelligent.
So the body tracking system, our RFID system, is telling in each and every station what model, what car, what style. As you can imagine, the sunroof is different than a full roof. A right steering wheel car is different than a left steering wheel car.
The data the RFID stores enables the robots to be programmed to make quite different models right next to each other.
So in total, there are 4 production lines in Wolfsburg. We are assembling not just the Volkswagen Tiguan and the Volkswagen Touran. We are assembling here also a car which is not labeled on a VW sign, the Seat Tarraco.
There are so many variations that the probability of 2 identical cars being made next to each other is minute.
Theoretically, it happens once a year that 2 twin cars are leaving the production of this facility.
Crucially, this adaptability future-proofs the plant, because it means that as soon as a new model is approved, it can go straight into production.
We're not just building cars at this facility, we have to keep ahead of the game. That means we always have to design and create new cars for our customers.
Every year, this mega car plant produces enough cars to create a traffic jam from New York to Los Angeles. One of the biggest challenges for mass-producing cars is maintaining demand.
The car market is incredibly competitive, and things are changing all the time.
And to design new cars and the best cars, we need to have the best facilities. We also do research and development processes here in the headquarters of Volkswagen.
They have a state-of-the-art research and development center right here at the Wolfsburg plant.
When you're designing a car, there are lots of different constraints. Some of them are just the laws of physics, but others are making sure that whatever it is you've designed is actually able to be manufactured. And that's why it's really important that the guys in R&D are talking with the people who are actually going to have to build the thing.
Having the designers and engineers in close proximity makes the evolution from concept car to mass production much faster.
Before a car goes into mass production, design does have to meet engineering. And at that point, the engineers get involved and will say, right, actually for this design to become reality, we're going to need to do ABC. There is a massive importance given to testing of prototypes. Precision down to every detail really matters. Having no gaps in the door and no sounds or no sound flushes at any point. Opening and closing doors, testing the suspension up and down in an actual environment. And that is really critical in today's environment.
Inside one of the most recent buildings at the plant is a $110 million test center that can analyze new designs 5 times faster than its predecessor. With high volumes of new models being made, any improvement can be very valuable, and any mistake can be disastrous.
Computer simulations are one thing, but the acid test is to put it in a wind tunnel.
In our original tunnel, we needed up to 30 minutes to load a car. And now we can manage it in under 5 minutes.
It's directly in the middle.
The wind tunnel at Wolfsburg is an absolute feat of engineering. It looks like something out of the future.
This tunnel is very fast. We can simulate driving at 155 miles per hour.
Generating this kind of wind speed requires a colossal state-of-the-art 3,000 kilowatt fan.
This is our fan with a diameter of 26 feet. This is the heart of our testing track.
The pressure to maximize performance is so high that the company broke the rules. Volkswagen's reputation was seriously damaged in 2015 after the company admitted installing software in millions of their cars to cheat emissions tests.
Volkswagen knew of these problems, and when regulators expressed concern, Volkswagen obfuscated, they denied, and they ultimately lied.
The scandal put top executives in jail, and VW had to pay more than $30 million in compensation. Despite this, in 2016, VW became the world's most successful car manufacturer by sales. But building huge numbers of cars creates yet another problem.
It's really critical to remember that the work does not end at the end of the line. We don't build cars just in case we sell them. You'd overrun the factory. There's only so much space available, and how much of that space do you really want to give to turn into a parking lot? You need a really efficient distribution system to move the car from the factory to the customer around the world.
A car can roll off the assembly line and be delivered to somewhere as far away as Shanghai at a phenomenal speed. Wolfsburg builds so many cars that simply shifting them off the site is an industry in itself.
The solution is pretty neat, if not challenging. The same network that brings in the raw materials brings the finished vehicles out, and that's principally the trains.
Every working day, about 1,800 cars leave the factory by freight train.
The challenge is to keep each train's waiting time to the minimum.
Conventionally, you'd use a process known as shunting, which is where you bring in an individual train carriage, load it up with cars, then drag it out again and couple it onto the rest of the train. And you can't do more than one of these carriages at a time. So it's incredibly long-winded and inefficient.
Instead, the Wolfsburg factory has a specially designed multiple loading bay.
We have a big advantage here, working with a sliding stage. It means that we can do 3 work processes at once.
First, cars are driven onto an empty carriage. Then the giant sliding stage moves the full carriage directly to the track, where the engine is waiting. At the same time, cars are driven onto the next empty carriage.
The upshot of this basically is that they can load multiple carriages in much quicker succession.
It enables super long trains to be assembled much faster than with traditional shunting. Every day, around 180 loaded carriages leave the factory. But not all customers want their cars delivered.
The Volkswagen decided, okay, let's invite the people to come here. And they opened the site for the customers and for the visitors.
Some can even collect their new car as soon as it comes off the assembly line.
The customer can be the very first person to sit behind the wheel and drive the car, which for some people is a real thrill.
A few cars travel along a tunnel without their odometers clocking up a single mile to one of the world's most high-tech car showrooms.
The advantage of these towers is that you can store loads of cars, but with a very small footprint on the ground.
But there's no drive ramp. So how do the cars get to their parking spaces? Inside each tower is an automated elevator. Powered by a pivoting 120 kilowatt motor with a 7.2-ton counterbalance, the mobile platform can lift cars and park them anywhere in the tower. It's the fastest automated high-rise parking system in the world.
Vertical system, it works very fast. It needs about 40 seconds, I think, to bring a car up or bring a car down and overhand it to the customer.
In manufacturing, no company can sit on its achievements. Volkswagen recently announced that it intends to invest $50 billion on new factory technology, with a significant amount going to Wolfsburg. As well as electric cars and new materials, they're also developing fully autonomous warehouse trucks.
They are able to make decisions effectively for themselves. They'll pick up material where it's required. They'll go to different stations as required. These are smarter, more efficient robots than we've seen before.
Whether this superstructure will go on to produce 1 million cars per year, only time will tell.
The agenda for Wolfsburg was to really build a car for everybody as cheaply as possible. So you could say that it began life wanting to make cars for the people, and now it wants to make cars for the world.
The plant may have had a dark history, and more recently been embroiled in scandal. But with its commitment to smart technology, it's still as ambitious as ever.